1. Mercury melts. Lead at noon, because of the sun. What would happen if you placed a block of lead on Mercury's surface at noon? It would melt into a shimmering puddle within minutes. Mercury, the planet closest to the sun, experiences temperatures so extreme they defy our understanding of what a planetary surface can endure. At its hottest point, Mercury's daytime surface reaches 430 degrees Celsius. To put this in perspective, lead melts at 327 degrees Celsius. Tin liquefies at 232 degrees. Even zinc, which requires 420 degrees to melt, would transform into liquid metal on Mercury's scorching plains. But here's what makes this truly strange. Mercury doesn't have the highest average temperature in the solar system. Venus holds that title. However, Mercury experiences the most extreme temperature variations of any planet. During its long night, temperatures plummet to minus 180 degrees Celsius. This represents a 610-degree difference between day and night. Why does this happen? Mercury sits just 58 million kilometers from the Sun. Earth orbits at 150 million kilometers, nearly 3 times farther. This proximity means Mercury receives about 7 times more solar energy per square meter than Earth. The Sun appears 3 times larger in Mercury's sky than in ours. Mercury's lack of atmosphere makes everything worse. Earth's atmosphere acts like a blanket, distributing heat around the planet and moderating temperature extremes. Mercury has virtually no atmosphere, just a thin exosphere of atoms stripped from its surface by solar radiation and micrometeorite impacts. This means there's nothing to retain heat at night and nothing to protect the surface from the sun's fury during the day. The planet's rotation adds another layer to this thermal nightmare. Mercury spins incredibly slowly. One Mercurian day from sunrise to sunrise lasts 176 Earth days. This means any point on the surface bakes under direct sunlight for 88 consecutive Earth days. Imagine standing in the same spot while the sun doesn't move for almost 3 months, getting hotter and hotter. Scientists discovered something unexpected about Mercury's rotation. The planet is locked in what's called a 3.2 spin-orbit resonance. For every 2 orbits around the Sun, Mercury rotates exactly 3 times on its axis. This unusual arrangement means some spots on Mercury's surface experience even more intense heating than others. There are locations near Mercury's equator, called hot poles, where the Sun appears to stop in the sky and even move backward briefly before continuing its path. These spots receive maximum solar heating. A thermometer placed there would measure temperatures approaching 450 degrees Celsius at peak heating. Despite these hellish conditions, Mercury has ice, inside permanently shadowed craters at the poles. Where sunlight never reaches, temperatures remain cold enough to preserve water ice. Some of these craters contain ice deposits several meters thick. The contrast is stunning. In one part of the planet, lead melts. A few hundred kilometers away, ice remains frozen for potentially billions of years. Mercury's surface bears the scars of this thermal stress. The extreme temperature cycle causes rocks to expand and contract repeatedly. Over billions of years, this has fractured and weakened surface materials. Cliffs hundreds of kilometers long have formed as the planet's interior cooled, and the entire world shrank slightly. Standing on Mercury at noon would be lethal in seconds. The intense heat would overwhelm any protective suit. The surface itself would radiate heat like the inside of a furnace. This small, airless world transforms solar energy into conditions more extreme than most places we can imagine. 2 solar storms create X-ray. Auroras on Jupiter. Have you ever seen an aurora that could kill you from space? Jupiter produces auroras so powerful they emit X-rays. These aren't the gentle green curtains of light that dance over Earth's polar regions. Jupiter's auroras are invisible monsters, releasing radiation that would be lethal to any unprotected observer nearby. Earth's auroras occur when charged particles from the sun collide with our atmosphere, exciting oxygen and nitrogen atoms that then release visible light. The process creates those beautiful green and red displays we see near the poles. Jupiter's auroras follow a similar principle, but everything about them exists on a scale that seems impossible. Jupiter's auroras carry hundreds of times more energy than Earth's entire aurora system. The total power reaches hundreds of gigawatts, equivalent to thousands of power plants running simultaneously. This energy doesn't just create visible light, It generates intense ultraviolet radiation and X-rays that telescopes like Chandra and XMM Newton can detect from Earth. But where does all this energy come from? Unlike Earth, which relies primarily on the solar wind for aurora activity, Jupiter generates much of its aurora power internally. The planet's rapid rotation, completing one full turn in just under 10 hours, creates an enormous magnetic field. This field is 20,000 times stronger than Earth's. Jupiter's volcanic moon, Io, plays a crucial role. Io's volcanoes spew about 1 ton of material per second. Sulfur, oxygen, and other elements gush into space, creating a massive torus of plasma around Jupiter. As Jupiter rotates, its magnetic field sweeps through this plasma, accelerating particles to extreme velocities. These accelerated particles spiral along magnetic field lines toward Jupiter's poles. When they collide with the upper atmosphere, they carry tremendous energy. The collisions occur at speeds exceeding 5,000 kilometers per second. At these velocities, the impacts generate temperatures reaching millions of degrees. The X-ray emissions were a mystery for years. Scientists couldn't understand which mechanism could accelerate particles to the extreme energies needed to produce X-rays. Recent observations revealed that the answer involves electromagnetic waves. These waves, called ion cyclotron electromagnetic waves, surf along Jupiter's magnetic field lines and progressively accelerate ions to increasingly higher energies. Jupiter's aurora oval covers an area larger than Earth's entire surface. The main oval remains permanently active, continuously glowing in ultraviolet wavelengths. Additional features called polar auroras flicker and pulse with remarkable complexity. Bright spots appear and disappear. Emission curtains stretch and contract. Solar storms make everything more intense. When a burst of solar wind hits Jupiter, it compresses the planet's magnetosphere. This compression triggers aurora storms that can last for days. X-ray emissions increase dramatically. The aurora expands and brightens. Additional features, called dawn storms, erupt on the dawn side of the planet. Scientists discovered something unexpected about Jupiter's X-ray auroras. They pulse with remarkable regularity, brightening every 27 minutes. This clockwork behavior suggests a fundamental oscillation in Jupiter's magnetosphere, some rhythmic process that periodically dumps energy into the aurora system. The other giant planets also have intense auroras. Saturn produces powerful ultraviolet auroras influenced by its ring system and moons. Uranus and Neptune show auroral activity despite their unusual magnetic field configurations. But Jupiter remains the undisputed champion, producing auroras of unmatched power and complexity. These invisible light shows reveal the violent environment around Jupiter. The radiation belts contain particles moving at nearly the speed of light. The magnetic field channels immense energy flows between the planet and its moons. Jupiter's aurora system represents one of the most extreme electromagnetic environments in the solar system, creating X-ray storms unlike anything on Earth. 3. Earth's magnetosphere compresses and expands daily. Did you know Earth has an invisible shield that breathes? Our planet's magnetosphere constantly changes size, compressing and expanding in response to the solar wind. This magnetic bubble that protects us from space radiation isn't static. It pulses with the rhythm of the sun's activity. The magnetosphere extends about 60,000 kilometers toward the sun on the day side. That's approximately 5 Earth diameters. On the night side, it elongates into a long tail called the magnetotail, reaching beyond the moon's orbit over 380,000 kilometers away. This asymmetric shape results from the constant pressure of the solar wind. Solar wind particles flow from the sun at velocities between 300 and 800 kilometers per second. When the supersonic stream of charged particles hits Earth's magnetic field, it cannot penetrate directly. Instead, it piles up and compresses the magnetic field on the day side. The interaction creates a shockwave in space, similar to the sonic boom created by a supersonic aircraft. But the solar wind isn't constant. It varies dramatically in speed, density, and magnetic field strength. When a calm period occurs with slow and steady solar wind, Earth's magnetosphere expands outward. The dayside boundary can move thousands of kilometers away from Earth. The magnetic field lines relax into a more rounded shape. Then a solar storm arrives. A coronal mass ejection or a fast stream of solar wind collides with the magnetosphere. The impact can be violent. Within minutes, the dayside magnetosphere compresses inward, sometimes by 20,000 kilometers or more. The magnetic field lines on the dayside get squeezed together, intensifying the magnetic field strength in that region. This compression has real consequences. Satellites orbiting in the outer magnetosphere can suddenly find themselves outside the protective bubble, exposed to intense radiation. During larger storms, the compression can be so severe that satellites in geostationary orbit, 36,000 kilometers up, experience dangerous radiation levels. The magnetosphere doesn't compress uniformly. The flanks, the sides of the magnetic bubble, ripple and churn as the solar wind flows past. These ripples, called surface waves or Kelvin-Helmholtz waves, look like ocean waves breaking on a beach. They can grow large enough to allow small amounts of solar wind plasma to enter the magnetosphere. Scientists monitor this breathing process constantly. Networks of spacecraft measure the solar wind upstream from Earth and track the magnetosphere's boundaries in real time. When instruments detect a strong solar wind disturbance approaching, they can predict when Earth's magnetic shield will compress and by how much. The magnetotail also responds to these changes. During compression, the tail contracts slightly on the night side. Energy builds up in the stretched magnetic field lines. Eventually, this stored energy is released. In a process called a substorm, the magnetic field lines snap back toward Earth, accelerating particles that create auroras and inject radiation into the inner magnetosphere. Ground-based magnetometers detect these changes. The instruments measure tiny variations in Earth's magnetic field strength. During larger compression events, the readings change visibly within minutes. Compass needles, if sensitive enough, would actually shift slightly as the magnetosphere compresses and expands. This daily breathing represents Earth's ongoing interaction with the Sun. Our magnetic shield constantly adjusts to changing space weather conditions. The magnetosphere expands during calm periods and contracts when solar storms hit it. This dynamic boundary between Earth's domain and interplanetary space never stops moving, never stops responding, never stops protecting us from space's radiation environment. 4. Solar wind rips. Comet tails millions of kilometers away. Why do comets have tails that always point away from the Sun? The answer reveals one of the most invisible and powerful forces in the solar system. The solar wind doesn't just blow through space, it literally tears material from comets, creating tails that extend for millions of kilometers. When a comet approaches the Sun, heat begins to vaporize its ice. Frozen water, carbon dioxide, methane, and other volatile compounds start to sublimate, transforming directly from solid to gas. This process releases dust that was trapped in the ice. The result is a cloud around the comet's nucleus called a coma. But the coma is just the beginning. The solar wind, that constant stream of charged particles emanating from the Sun at velocities of 400 to 800 kilometers per second, collides with the gas and dust around the comet. This collision creates not one but two distinct tails. The ion tail forms when the solar wind ionizes gas molecules in the coma. These charged molecules are then pushed by the magnetic field embedded in the solar wind. The result is a perfectly straight, bluish tail that points directly away from the Sun. This tail can extend for 100 million kilometers or more, nearly the distance from Earth to the Sun. The dust tail follows a different trajectory. Dust particles released from the nucleus aren't affected by the solar wind's magnetic field. Instead, solar radiation pressure, the physical force of sunlight pushing against the particles, drives them backward. Because these particles have mass, they follow curved trajectories as the comet moves in its orbit. What makes this truly fascinating is how quickly these tails form and change. As a comet approaches the Sun, its tails grow dramatically. A comet that had tails of just a few thousand kilometers in the outer solar system can develop tails tens of millions of kilometers long as it passes by the Sun. Ion tails are particularly dynamic. They respond in real time to changes in the solar wind. When a burst of solar wind hits a comet, the ion tail can brighten more intensely. During disconnection events, the entire tail can break off, and a new one begins to form. Observations have shown tails being completely torn away and replaced within hours. Comet Hyakutake, which passed near Earth in 1996, had its ion tail measured at over 570 million kilometers long. That's more than 3 times the distance from Earth to the Sun. The tail was so long it extended beyond Mars's orbit. This record tail was created entirely by the action of the solar wind tearing away ionized material. Detailed observations revealed complex structures in comet tails. Rays, knots, and kinks appear in the ion tail, showing turbulence and magnetic instabilities. These features change on timescales of minutes to hours, providing scientists with a real-time visualization of how the solar wind interacts with objects in space. The tail's direction proves something fundamental about the solar wind. Long before we had spacecraft to measure the solar wind directly, astronomers noticed that comet tails always pointed away from the sun, no matter which direction the comet was traveling. This could only mean that something was flowing radially outward from the sun, pushing the tails. Comets that pass near the sun experience even more extreme forces. Sun-grazing comets, which plunge within the solar corona, can have all their material stripped away within hours. Some survive the journey, emerging with spectacular tails. Others disintegrate completely, vaporized by heat and torn apart by tidal forces and solar wind. Each comet that enters the inner solar system becomes a natural laboratory. The tails reveal the strength, velocity, and magnetic structure of the solar wind. They show how objects interact with the constant flow of particles from the sun. And they demonstrate that the solar wind is real, powerful, and capable of tearing material from objects millions of kilometers away. 5. Jupiter's auroras are 100 times more powerful than Earth's. Imagine an aurora so powerful it covers an area larger than the entire planet Earth. Jupiter produces exactly that. The auroras at Jupiter's poles aren't just bigger versions of the northern lights. They represent one of the most violent electromagnetic phenomena in the solar system, releasing energy on scales that defy imagination. The most powerful terrestrial aurora ever recorded released about 1 trillion watts of energy. Impressive, right? Jupiter's auroras continuously release hundreds of trillions of watts. That's hundreds of times more energy than all of Earth's auroras combined during an intense magnetic storm. Why does Jupiter produce such extraordinary auroras? The answer begins with the planet's magnetic field. Jupiter rotates on its axis every 9.9 hours, an incredibly rapid rotation for such a massive planet. This rapid rotation, combined with currents of liquid metal in the planet's deep interior, generates a powerful magnetic dynamo. The resulting magnetic field extends millions of kilometers into space. If you could see it from Earth, Jupiter's magnetosphere would appear several times larger than the full moon in the sky. Within this vast magnetic region, charged particles are accelerated to tremendous energies. Io, Jupiter's volcanic moon, adds fuel to the fire. Io's volcanoes eject about 1 ton of material per second into space. This material, mainly sulfur dioxide, oxygen, and sulfur, forms a giant torus of plasma around Jupiter. As the planet rotates, its magnetic field sweeps through this plasma like a giant beater. The captured particles are accelerated along magnetic field lines toward Jupiter's poles. When they hit the upper atmosphere, they're traveling at 5,000 kilometers per second or more. The impact generates temperatures exceeding 1 million degrees Celsius. At these temperatures, hydrogen atoms in the atmosphere emit intense ultraviolet light. Jupiter's main aurora oval is about 30,000 kilometers in diameter. The entire Earth could fit comfortably inside this glowing ring. And unlike Earth's auroras, which appear and disappear with solar activity, Jupiter's main oval glows permanently. It's a permanent feature, always active, always releasing massive energy. Observations with the Hubble Space Telescope revealed extraordinary complexity. Within the main oval, bright spots appear linked to Jupiter's moons. Io, Europa, and Ganymede each leave an auroral footprint where their interaction with Jupiter's magnetic field channels particles into the atmosphere. Io's footprint glows brightest, moving through the aurora as Io orbits. Jupiter's auroras also emit X-rays. Earth produces weak and occasional auroral X-rays. Jupiter produces them continuously and with much greater intensity. For years, scientists wondered how particles were accelerated to the extreme energies needed to create X-rays. The answer involves electromagnetic waves that surf along magnetic field lines, repeatedly accelerating heavy ions like oxygen and sulfur. Solar storms amplify the spectacle. When a coronal mass ejection hits Jupiter, the magnetosphere compresses. This triggers even brighter and more expansive aurora events. X-ray emissions increase. Features called polar storms appear, creating complex and constantly changing emission patterns. Scientists discovered that Jupiter's auroras pulse with surprising regularity. X-ray emissions increase and decrease every 27 minutes like clockwork. This rhythm suggests that some fundamental process in Jupiter's magnetosphere oscillates regularly, periodically dumping energy into the aurora system. The Juno spacecraft orbiting Jupiter since 2016 provided unprecedented views of the auroras from above. Its instruments measured the incoming particles, the magnetic field, and the auroral emissions simultaneously. The data confirmed that particles with energies up to 400,000 electron volts collide with the atmosphere, creating the most powerful displays. Comparing Jupiter's and Earth's auroras reveals fundamental differences. Earth relies primarily on the solar wind for its auroral activity. Jupiter generates most of its own auroral energy through its rapid rotation and volcanic moons. Earth produces beautiful and occasional lights. Jupiter operates a permanent, powerful, and unmatched aurora machine. 6. Saturn's rings glow differently. According to solar activity, did you know Saturn's rings change appearance when the sun is active? These iconic rings aren't static, unchanging structures. They respond to solar activity in subtle but detectable ways, changing their brightness and electrical properties as solar storms hit them. Saturn's rings consist of billions of ice particles, ranging in size from sand grains to houses. These particles orbit Saturn in a thin layer extending hundreds of thousands of kilometers but only a few tens of meters thick in most places. Under normal conditions, they reflect sunlight in relatively predictable ways. But something interesting happens when the sun is particularly active. During solar storms, the flux of charged particles and ultraviolet radiation hitting the rings increases dramatically. This radiation interacts with the ice particles in complex ways, altering their surface properties. Solar ultraviolet radiation can ionize molecules on the ice particle's surface. When this happens, the particles develop electrical charges. Charged particles interact differently with light than neutral particles. They also interact with each other through electrostatic forces, causing some particles to repel slightly. Observations from the Cassini probe, which orbited Saturn from 2004 to 2017, detected these changes. Instruments measured variations in ring brightness correlated with solar activity. During periods of high solar activity, certain ring regions reflected light slightly differently. The changes were subtle, usually just a few %, but consistent and measurable. The Cassini division, that prominent gap in the rings visible even from Earth-based telescopes, proved particularly sensitive. Tiny dust particles in this region responded more strongly to electrical charging than larger ice particles. When solar activity increased, these dust particles changed their distribution slightly, affecting how the division appeared. Saturn's magnetic field adds another layer of complexity. Charged particles in the rings don't exist in isolation. They orbit within Saturn's magnetosphere, interacting with the planet's magnetic field. When solar storms compress Saturn's magnetosphere, conditions around the rings change, affecting how charged particles behave. Scientists discovered that the rings can even develop their own localized electric fields. In regions where many particles become charged, collective electric fields form. These fields are weak but can be strong enough to influence very small dust particles, causing them to move up or down relative to the main ring plane. Solar radiation also affects the ice surface chemistry. High-energy ultraviolet photons can break apart water molecules on the ice particle's surface. This creates free radicals and other reactive chemical species. During periods of high solar activity, more of these reactions occur, potentially altering the ice particle's surface properties. The most dramatic phenomenon occurs when a large coronal mass ejection hits Saturn. The sudden increase in charged particles and radiation can temporarily alter the ring's appearance more noticeably. Observations during such events showed brightness changes of up to 10% in some regions, with effects lasting hours to days. The spokes in the rings, those dark radial marks that appear and disappear, are also influenced by solar activity. These spokes are caused by tiny electrically charged dust particles lifting above the ring plane. The rate at which spokes form increases during periods of higher solar activity, when more particles become charged. This sensitivity to solar activity makes Saturn's rings a type of space weather detector. By observing how the rings respond, scientists can learn about radiation conditions around Saturn. The rings provide a visible screen where the invisible effects of solar activity become apparent. The 11-year solar cycle leaves its mark on the rings. During solar maximum, when the sun is most active, the rings experience more variability. During solar minimum, when the sun is calm, the rings show fewer changes. This long-term modulation means Saturn's rings look subtly different at different phases of the solar cycle, a reminder that even the most iconic planetary structures aren't immune to our star's influence. 7. Uranus has auroras in the wrong places because of the sun. What happens when a planet tips on its side and the sun tries to create auroras? You get one of the strangest light shows in the solar system. Uranus produces auroras that appear in the most unexpected places, creating patterns that defy everything we learned by observing auroras on Earth and other planets. Uranus orbits the sun tipped on its side. Its rotation axis is tilted 98 degrees, meaning the planet essentially rolls along its orbit like a ball. This bizarre orientation already makes Uranus unique, but the real weirdness begins when you consider its magnetic field. Uranus's magnetic field doesn't align with its rotation axis, not even close. The magnetic axis is tilted 59 degrees relative to the rotation axis. For comparison, Earth's magnetic field is tilted just 11 degrees from its rotation axis. This huge tilt means Uranus's magnetic poles aren't anywhere near its geographic poles, but it gets even stranger. The center of Uranus's magnetic field isn't at the planet's center. It's offset by about 1/3 of the planet's radius. Imagine a bar magnet inside Uranus, but instead of being at the center, it's pushed to the side and tilted at a crazy angle. That's basically Uranus's magnetic field. When the solar wind hits this chaotic magnetic field, the result is auroras that appear in completely unexpected locations. Instead of organized aurora ovals around the geographic poles like we see on Earth, Uranus's auroras appear at strange latitudes. Sometimes they occur near the equator, other times they appear at intermediate positions that make no intuitive sense. The Hubble Space Telescope captured images of these bizarre auroras in 2011 and again in 2014. The observations showed bright spots of ultraviolet emission appearing far from where auroras should be. As Uranus rotated, these auroral spots moved across the planet's disk in ways that seemed almost random. The key to understanding these auroras lies in recognizing that auroras always follow magnetic field lines. Charged particles spiral along these magnetic lines until they hit the atmosphere. On planets with neatly aligned magnetic fields, this creates aurora ovals around the magnetic poles. But Uranus's misaligned and off-center magnetic field creates field lines that connect to the atmosphere in bizarre locations. As Uranus rotates every 17.2 hours, its magnetic field twists and turns relative to the solar wind flow. Imagine trying to create auroras on a planet where the magnetic poles spin completely through the solar wind region every day. The connections between the solar wind and the magnetosphere change dramatically hour by hour. During Voyager 2's visit in 1986, Uranus's south pole was pointing almost directly at the sun. This created a configuration where the solar wind collided head-on with one of the magnetic poles. But due to the magnetic field's misalignment, this magnetic pole wasn't where the geographic pole was. The result was a magnetospheric geometry unlike any other ever observed. Recent observations revealed that Uranus's auroras pulse and change rapidly. Within minutes, auroral spots can appear, brighten intensely, and then disappear. This rapid variability suggests the connection between the solar wind and Uranus's magnetosphere is highly dynamic and unstable. The misaligned magnetic field also means different parts of Uranus's magnetosphere experience drastically different conditions over the course of a Uranian day. One region might be connected to the solar wind and experiencing particle input, while just a few hours later that same region is shielded and quiet. It's like having space weather that changes completely several times per day. Scientists believe Uranus's strange magnetic field may be generated in a layer of electrically conducting water, ammonia, and methane somewhere between the core and atmosphere. Unlike Earth, where the magnetic field comes from a molten iron core, Uranus may have its magnetic dynamo operating in an outer shell. This would explain why the field is so misaligned and off-center. The end result is that Uranus has auroras like no other planet. They appear in the wrong places, move in unpredictable ways, and defy our expectations about how auroras should behave. Each time we observe Uranus, we see a reminder that the universe is stranger and more varied than our theories often predict. 8. Neptune receives 900 times less light, but still has solar storms. How can a planet be affected by the sun when it's so far away that sunlight is almost negligible? Neptune orbits 30 times farther from the sun than Earth. At this distant reach, sunlight is 900 times weaker than we experience here. Yet Neptune still feels the sun's influence through solar storms that travel billions of kilometers through space. Neptune sits 4.5 billion kilometers from the sun. To put this in perspective, sunlight takes over 4 hours to reach Neptune. If you could stand on Neptune's surface, if it had one, the sun would look like just a very bright star in the sky, not the radiant disk we see from Earth. At this distance, you'd expect the solar wind to have spread out so much it would be practically non-existent. And it's true that the solar wind at Neptune is much more tenuous than near Earth. The density of solar wind particles decreases with the square of the distance from the sun. At Neptune, there are about 900 times fewer particles per cubic meter than near Earth. But the solar wind still gets there. And when the sun produces a particularly powerful coronal mass ejection, these plasma clouds travel through the entire solar system. They take days or even weeks to reach Neptune, but when they arrive, they still carry enough energy to affect the planet's magnetosphere. Neptune has a strong magnetic field, similar to Uranus in its weirdness. The magnetic field is tilted 47 degrees relative to the rotation axis and offset from the planet's center. This magnetic field creates a magnetosphere that interacts with the solar wind, even at this extreme distance. Observations showed that Neptune experiences auroras. The Hubble Space Telescope detected ultraviolet emissions consistent with auroral activity at Neptune's magnetic poles. These auroras are generated when solar wind particles, even at these low densities, are channeled along magnetic field lines into the atmosphere. What makes this truly remarkable is that any effect is detectable at all. The solar wind particles have traveled so far and spread out so much that you'd think they'd be insignificant. But Neptune's magnetosphere is sensitive enough to capture these sparse particles and create visible auroras. Solar storms create disturbances in Neptune's magnetosphere just as they do near Earth. When a strong coronal mass ejection finally reaches Neptune's orbit, it compresses the planet's magnetosphere. The sudden pressure triggers the same types of processes we see closer to the sun: magnetic reconnection, particle acceleration, and intensified auroras. The Voyager 2 spacecraft provided the only close visit to Neptune in 1989. During its flyby, instruments measured the magnetosphere and detected signs of interaction with the solar wind. The data confirm that even at this remote distance, the connection between Neptune and the sun remains active. Long-term observations revealed something surprising. The intensity of Neptune's auroras varies with the 11-year solar cycle. During solar maximum, when the sun is most active and producing more coronal mass ejections, Neptune's auroras are slightly brighter and more frequent. During solar minimum, they weaken. This means that even at 4.5 billion kilometers away, Neptune can feel whether the sun is in an active or calm period. The connection spans the entire solar system. Storms that erupt on the sun's surface eventually, weeks later, create measurable effects in Neptune's magnetosphere. The solar wind at Neptune also remains supersonic. Even after traveling through the entire solar system, the particles are still moving faster than the speed of sound in plasma. This means there's still enough energy to create shockwaves and other plasma phenomena when they interact with Neptune's magnetosphere. Scientists use Neptune as a natural laboratory to study how the solar wind behaves at the outer edges of the solar system. Observations of Neptune help map how far the sun's influence extends. The answer, apparently, is at least to Neptune and probably far beyond. The Voyager probes, now in interstellar space beyond Pluto, still detect the solar wind. This confirms the sun's influence extends well beyond Neptune. The heliosphere, the bubble of solar influence, reaches about 120 times the Earth-Sun distance. Neptune orbits within this bubble, still firmly in the sun's domain. The connection between Neptune and the sun demonstrates something profound about our solar system. It's not a collection of isolated planets floating independently. It's a connected system where events on the sun create ripples that propagate outward, eventually reaching even the most distant members of the planetary family. Even in the cold darkness of the outer regions, the sun's presence is still felt. 9. Pluto's tail changes direction as it orbits. Pluto may be small, but it has something Earth doesn't: a tail. During part of its orbit, Pluto develops an atmosphere that escapes into space, creating a comet-like tail that always points away from the sun. And as Pluto travels in its elliptical orbit, this tail changes direction in fascinating ways. Pluto's orbit is highly elliptical. At its closest point to the sun, called perihelion, Pluto reaches 4.4 billion kilometers from the sun. At the farthest point, aphelion, it stretches away to 7.3 billion kilometers. This nearly 3 billion kilometer difference creates dramatic changes in the conditions Pluto experiences. When Pluto is closest to the sun, the faint sunlight warms its surface. Pluto is covered primarily by frozen nitrogen, methane, and carbon monoxide. When these ices warm up, even slightly, they begin to sublimate, transforming directly from solid to gas. The result is a tenuous atmosphere extending hundreds of kilometers above the surface. But this atmosphere doesn't stay trapped by gravity. Pluto is small, with only 1/6 the mass of the Moon. Its gravity is too weak to firmly hold atmospheric gases. As gas molecules escape into space, they form a tail of material extending behind Pluto in its orbit. The solar wind, even at this extreme distance, pushes this escaping atmosphere. Just like comet tails, Pluto's tail points away from the sun. But unlike a comet, which might pass by the sun in a matter of weeks, Pluto takes 248 Earth years to complete one orbit. This means the tail's direction changes very slowly as Pluto travels around the sun. The New Horizons probe, which flew by Pluto in 2015, provided direct evidence of this escaping atmosphere. Instruments detected nitrogen escaping into space at a rate of about 500 tons per hour. This might sound like a lot, but Pluto can sustain this loss for billions of years without depleting its vast nitrogen ice deposits. New Horizons data revealed that Pluto's atmosphere extends much farther than scientists expected. The exosphere, the outermost atmospheric layer, reaches about 1,600 kilometers above the surface. That's approximately 1/10 of Pluto's diameter. No other solid object in the solar system, except active comets, has such an extensive atmosphere relative to its size. The atmospheric escape rate varies as Pluto moves in its orbit. When Pluto is closest to the sun, more ice sublimates and the atmosphere grows thicker. The escape rate increases. Pluto's tail grows longer and denser. When Pluto moves away from the sun, temperature drops, less ice sublimates, and the atmosphere begins to dissipate. Scientists predict that when Pluto is at its aphelion, the farthest distance from the sun, the atmosphere may completely freeze back onto the surface. Pluto spends about 20 years of its orbit in this cold region. During this period, the atmosphere collapses and the tail disappears. Pluto temporarily becomes an airless world. Pluto's last perihelion occurred in 1989. Since then, Pluto has been slowly moving away from the sun. Ground-based observations detected that the atmosphere is gradually becoming more tenuous. Eventually, in the coming decades, the atmosphere may collapse completely until Pluto returns closer to the sun again in about a century. The tail's direction reveals something fundamental about the solar wind's nature. Even at 5 billion kilometers from the sun, the solar wind still flows radially outward. It still carries enough force to push light gases away from the sun. Pluto's tail serves as a cosmic weather vane, always pointing in the direction of the solar wind flow. Observing how Pluto's tail changes over decades and centuries would provide valuable information about the solar wind's long-term variability. Unfortunately, Pluto is so distant and its tail is so tenuous that detecting it from Earth is extremely difficult. New Horizons provided a snapshot during its flyby, but long-term studies would require dedicated missions. Pluto's seasonal atmosphere, expanding and contracting over centuries, creates a cycle unlike any other planet. Earth has seasons lasting months. Pluto has seasons lasting decades to centuries. And with these seasons come fundamental changes: the presence or absence of an atmosphere, and the formation and dissipation of a tail pointing eternally away from the distant sun. 10. The asteroid belt is swept by invisible solar storms. Between Mars and Jupiter, hundreds of millions of space rocks orbit the sun. The asteroid belt seems like a quiet, unchanging place. but this region is constantly swept by invisible solar storms that affect these objects in ways we've only recently begun to understand. The asteroid belt extends from about 2.2 to 3.2 times Earth's distance from the Sun. In this region, the solar wind still flows strong, traveling at velocities of 400 to 600 kilometers per second. When coronal mass ejections pass through the belt, they create magnetic disturbances and shock waves that wash over every asteroid. Most asteroids don't have magnetic fields of their own. They're just inert rocks tumbling through space. But that doesn't mean they're immune to the solar wind's effects. Radiation and charged particles from the Sun interact with their surfaces in subtle but important ways. The solar wind constantly bombards asteroid surfaces with charged particles. Over millions of years, this bombardment alters the surface chemical composition. Minerals that would be stable in an Earth laboratory slowly degrade under the relentless assault of high-energy protons and electrons. This process, called space weathering, darkens asteroid surfaces. It creates an altered layer of material that can be centimeters to meters deep. When scientists compare light spectra reflected from asteroids with meteorite samples in laboratories, they often find differences. The asteroid surface appears darker and redder than the pristine material inside meteorites. Solar storms intensify this process. During a major coronal mass ejection, the flux of energetic particles increases dramatically. Within hours to days, an asteroid can receive as much radiation as it normally would in months. These radiation bursts accelerate weathering, creating detectable changes on human timescales. Some asteroids have surface compositions that make them particularly sensitive to the solar wind. Carbonaceous asteroids, rich in organic compounds and hydrated minerals, respond strongly. Radiation can break down complex organic molecules, alter mineral crystal structure, and even release trapped water molecules. Telescopic observations detected changes in asteroid reflectivity that correlate with large solar events. After particularly intense solar storms, some asteroids appear slightly darker or have slightly altered spectra. These changes are small, but with modern instruments sufficiently sensitive, they're measurable. The asteroid belt also experiences the equivalent of auroras, though of a very strange type. When energetic particles from the Sun collide with very tenuous gas molecules around some asteroids, they can create faint emissions. Asteroids like Ceres, which has water molecules escaping from its surface, show evidence of these particle-induced emissions. Solar radiation also creates electrical charges on asteroid surfaces. The Sun-facing side accumulates positive charge as photoelectrons are ejected by ultraviolet light. The night side may accumulate negative charge as solar wind electrons deposit. These charge differences create weak electric fields that can affect dust particles on the surface. Spacecraft missions to asteroids provided direct evidence of these processes. The Near-Shoemaker probe orbited asteroid Eros and detected X-ray emissions. These emissions were created when solar X-rays hit the surface and made atoms release their own fluorescent X-ray radiation. The emission intensity varied with solar activity. The Hayabusa 2 mission to asteroid Ryugu and OSIRIS-REx to asteroid Bennu both revealed surfaces much darker than expected. Analyses suggest that intense space weathering, driven by decades to millions of years of solar wind exposure, created these darkened surfaces. When return samples are analyzed, the interior material is brighter, confirming the surface was altered. The interplanetary magnetic field embedded in the solar wind also affects the asteroid belt. This field creates a background magnetic environment that varies with solar activity. During periods of high activity, the field becomes more turbulent and variable. During quiet periods, it becomes more ordered. These variations can influence how charged particles interact with asteroid surfaces. Understanding how solar storms affect asteroids has practical implications. If humans someday mine asteroids or establish bases on them, they'll need to protect equipment and people from radiation. Asteroids have no atmospheres or magnetic fields to provide protection. During major solar storms, radiation levels on asteroid surfaces would increase to dangerous levels within hours. The asteroid belt serves as a natural laboratory to study how airless objects respond to solar radiation. Each asteroid is a different experiment, with unique composition, size, and orbital history. Together, they reveal that even regions of space that seem empty and quiet are actually dynamic, constantly being reshaped by invisible forces emanating from the Sun. 11. Mercury has a comet-like tail. Created by the solar wind, Mercury isn't just a planet, it's also, strangely, a comet. Mercury has a tail extending millions of kilometers behind it as it orbits the Sun. This tail isn't made of vaporized ice like comet tails. It's made of sodium atoms torn from the surface by the relentless force of the solar wind. The discovery of Mercury's tail was a total surprise. In 2001, astronomers using ground-based telescopes detected an elongated cloud of glowing sodium atoms following Mercury in its orbit. The tail extended over 2.5 million kilometers, about 6 times the Earth-Moon distance. How does the solar wind create this tail? Mercury has no substantial atmosphere to protect its surface. The solar wind hits the ground directly with full force. When high-energy charged particles collide with surface rocks, they transfer enough energy to eject individual atoms. This process, called sputtering, works like atomic-level bombardment. A proton or ion from the solar wind colliding with the surface can knock loose several atoms. Over billions of years, the solar wind has literally stripped away layers of material from Mercury's surface. Atom by atom, sodium is particularly visible because it glows brightly at specific yellow wavelengths when excited by sunlight. Other elements are also stripped from the surface, including potassium, calcium, and magnesium, but sodium dominates observations because it's easier to detect. The tail's intensity varies dramatically. When Mercury is at its perihelion, the closest point to the Sun, the tail glows most brightly. At this position, the solar wind is strongest, and solar radiation most intense. More atoms are ejected from the surface and the tail becomes more prominent. At aphelion, when Mercury is farthest, the tail weakens. The tail's shape also changes based on solar wind conditions. During solar storms, when particularly intense solar wind bursts hit Mercury, the sputtering rate increases dramatically. The tail can glow several times more brightly during these storms, creating a visible signal of space weather. The MESSENGER probe, which orbited Mercury from 2011 to 2015, studied the tail in unprecedented detail. Instruments mapped the distribution of sodium, potassium, and other elements. The data revealed that the tail has complex structure with patches and streamers that change over hours and days. MESSENGER discovered that the tail creation process is more complicated than just solar wind sputtering. Micrometeoroids hitting the surface also release atoms. Sunlight can directly vaporize some materials, and chemical processes on the surface, driven by intense solar radiation, can release atoms as well. The tail has 2 main components. A narrow, concentrated tail extends directly away from the Sun, created by solar radiation pressure pushing sodium atoms. A second, broader component results from atoms being ionized by the Sun and then swept away by the solar winds. Magnetic field. Observations showed that the tail pulses and varies on surprisingly short timescales. Within hours, the intensity can double or drop by half. These rapid variations reflect changes in solar wind conditions and also possible variations in the rate at which atoms are released from different regions of Mercury's surface. The tail's existence means Mercury is slowly losing material to space. The loss rate is minuscule on human timescales, just a few kilograms per second. But over billions of years, this adds up. Calculations suggest Mercury may have lost a layer of material several meters deep across its entire surface over the solar system's age. This loss affects our interpretation of Mercury's surface composition. The surface we see today may not represent the original composition. Volatile elements that are more easily ejected may have been preferentially removed, leaving behind a surface enriched in more resistant elements. Mercury's tail becomes most dramatic near perihelion, which occurs every 88 Earth days. During these close passages, Mercury is just 46 million kilometers from the Sun, experiencing about 11 times the solar radiation intensity that Earth receives. The combined bombardment of intense radiation and dense solar wind creates the most extreme conditions. Observing Mercury's tail provides information about the solar wind itself. Changes in the tail reflect changes in the solar wind's velocity, density, and composition. Mercury acts as a natural space weather detector, its tail brightening and fading in response to solar conditions. This phenomenon places Mercury in a unique category. It's a planet with comet-like properties, creating a tail through processes completely different from those operating in true comets. Where comets sublimate ice, Mercury is stripped atom by the relentless force of radiation from the nearest sun. 12. Io, Jupiter's moon, has auroras caused by the solar magnetic field. Imagine a moon so electrically connected to its planet that it carries currents of millions of amperes. Io, Jupiter's volcanic moon, doesn't just orbit the giant planet, it's electrically connected to it through an invisible magnetic flux tube that channels tremendous energy, creating auroras on both Io and Jupiter. Io orbits deep within Jupiter's powerful magnetosphere. The magnetic field there is 20,000 times stronger than Earth's magnetic field. Io, with its hundreds of active volcanoes, constantly ejects material into space. About 1 ton of sulfur dioxide, sulfur, and oxygen gushes from Io's volcanoes every second. This material doesn't fall back to Io. It enters orbit around Jupiter, forming a massive plasma torus. As Jupiter rotates every 10 hours, its magnetic field sweeps through this plasma, but Io orbits more slowly, taking 42 hours to complete one orbit. This creates relative motion between Io and the magnetized plasma around it. The result is a powerful electromagnetic interaction. Io acts like an electrical generator, moving through Jupiter's magnetic field lines. This movement generates an electrical potential difference of about 400,000 volts across Io. Electrical currents of up to 3 million amperes flow between Io and Jupiter's atmosphere along the magnetic field lines. These currents create auroras on both Io and Jupiter. On Io itself, charged particles accelerated along the magnetic field lines collide with Io's tenuous sulfur dioxide atmosphere. The collisions create auroral emissions that glow in ultraviolet and visible wavelengths. Io's auroras appear mainly near the moon's magnetic poles, where Jupiter's magnetic field lines enter and exit. Observations with the Hubble Space Telescope revealed bright spots of ultraviolet emission at these locations. The auroras pulse and change as Io moves through different regions of Jupiter's magnetosphere. But the most spectacular effect occurs on Jupiter. The currents flowing from Io travel along magnetic field lines to Jupiter's upper atmosphere. There, the charged particles create a bright aurora spot at Io's magnetic footprint. This footprint appears as a bright oval spot that moves across Jupiter's aurora as Io orbits. Io's auroral footprint on Jupiter is surprisingly complex. It's not just a single spot. It's a structure with multiple features, a bright main spot, and an emission tail extending downstream. The tail can extend hundreds of kilometers across Jupiter's aurora, created by disturbances in the magnetosphere triggered by the interaction with Io. The total power dissipated in this system is impressive. An estimated 1 to 2 trillion watts of energy flow through the Io-Jupiter electrical circuit. That's approximately equal to all of human civilization's electricity output being continuously dissipated in this single moon-planet system. The solar wind, even hitting Jupiter, influences this process. When solar storms compress Jupiter's magnetosphere, conditions around Io change. The strength of electrical currents can increase. The auroras on both Io and Io's footprint on Jupiter can glow more brightly. The entire system responds to variations in space weather. Europa and Ganymede, other moons of Jupiter, also create auroral footprints, but smaller and fainter than Io's. Io dominates because it ejects much more material and orbits deeper within Jupiter's magnetosphere, where the magnetic field is stronger. The Io-Jupiter electrical connection represents a type of phenomenon that doesn't exist on Earth. We don't have large moons orbiting through our magnetosphere. But at Jupiter, this interaction creates one of the most powerful natural electrical circuits known in the solar system. Detailed observations revealed that Io's footprint varies as Io moves through different regions of Jupiter's magnetosphere. When Io crosses through dense plasma regions, the footprint glows more brightly. When it passes through emptier regions, it weakens. These variations provide information about Jupiter's magnetosphere structure. The Juno spacecraft, currently orbiting Jupiter, passed directly through Io's auroral footprint. Instruments measured the energetic particles, electric and magnetic fields in this region. The data confirmed that particles with energies of tens of thousands of electron volts are precipitating into the atmosphere, creating the auroral emissions. This system demonstrates that auroras aren't just about the sun hitting planets. In giant planet systems with large moons, the moons themselves can play important roles in creating auroras. Io, with its powerful volcanoes and position within Jupiter's magnetosphere, has essentially created its own aurora machine. electrically connecting to its giant planet in ways that continue to surprise scientists. 13. Solar tornadoes, taller than 40 Earths. What would you call a rotating column of superheated plasma rising from the sun's surface to heights that would make 40 stacked Earths look small? Scientists call them solar tornadoes, but these phenomena make any terrestrial tornado seem like a gentle breeze in comparison. Solar tornadoes were first observed in detail by NASA's Solar Dynamics Observatory spacecraft. The images revealed enormous columns of hot gas spinning violently, rising from the sun's surface into the corona. Some of these structures reach heights of 200,000 kilometers or more. For comparison, Earth's diameter is about 12.7 thousand kilometers. These tornadoes aren't really tornadoes in the meteorological sense. Terrestrial tornadoes are driven by atmospheric pressure differences. Solar tornadoes are powered by magnetic forces. Twisted and coiled magnetic fields on the sun's surface create rotating columns of plasma that are channeled upward along magnetic field lines. The rotation is real, though. Observations show gas swirling around these structures' central axis at velocities up to 300,000 kilometers per hour. That's about 1,000 times faster than the strongest winds in terrestrial tornadoes. At this speed, the gas could travel from Earth to the Moon in less than an hour. The temperature inside these solar tornadoes ranges from about 50,000 to over 2 million degrees Celsius. The lower end, where the tornado connects to the sun's surface, is relatively cool at about 5,500 degrees. But as plasma rises through the chromosphere and enters the corona, temperatures increase dramatically. Why do they form? The answer lies in the turbulent nature of the sun's magnetic field. The sun doesn't rotate as a solid body. The equator rotates faster than the poles. This differential rotation twists and coils magnetic field lines like rubber bands being twisted. Eventually, these coiled field lines organize into helical structures. Conductive plasma is forced to follow these twisted magnetic field lines. The result is rotational motion. Gas spirals upward along the magnetic field, creating the appearance of a tornado. But unlike terrestrial tornadoes, which last minutes to hours, solar tornadoes can persist for days. Observations show that these tornadoes frequently appear near active regions on the sun's surface, areas with particularly strong and complicated magnetic fields. They also appear at prominences, those large arch-shaped structures of plasma that rise from the solar surface. The mass of plasma contained in a single solar tornado is impressive. Estimates suggest some contain billions of tons of material. This enormous mass is all in rotational motion, creating tremendous angular momentum. If it could be harnessed, the kinetic energy in a single solar tornado would exceed humanity's entire energy output for thousands of years. Solar tornadoes don't form randomly. They appear in patterns related to the sun's underlying magnetic structure. Where magnetic field lines emerge from the surface at certain angles and configurations, tornadoes are more likely to form. This allows scientists to predict to some extent where and when these phenomena will appear. Sometimes solar tornadoes become unstable. The magnetic field sustaining them can undergo reconnection, suddenly releasing stored energy. When this happens, the tornado can erupt, launching its contents into space in a coronal mass ejection. Billions of tons of plasma that were spinning in an organized column suddenly become an expanding cloud traveling at millions of kilometers per hour. These tornadoes' height reveals something important about the sun's atmosphere. The corona extends much farther than the visible surface. Tornadoes reaching 40 Earth diameters demonstrate that the solar atmosphere is thick, complex, and capable of supporting enormous vertical structures. Observing solar tornadoes at different light wavelengths reveals their layered structure. In extreme ultraviolet light, you see the hottest plasma in the corona. At hydrogen alpha wavelengths, you see cooler layers closer to the surface. Combining these observations, scientists can map these phenomana's complete three-dimensional structure. Solar tornadoes also produce waves. As they rotate, they send magnetohydrodynamic waves through the surrounding plasma. These waves propagate energy and can affect distant regions of the solar atmosphere. Some scientists believe these waves may contribute to coronal heating, helping solve the mystery of why the sun's atmosphere is hotter than its surface. Each solar tornado is unique. Some are straight and vertical, others curve and snake. Some spin clockwise, others counterclockwise, depending on the local magnetic field configuration. Together, they demonstrate that the sun's surface is a place of perpetual motion, continuous violence, and phenomena operating on scales that defy human comprehension. 14. The coronal heating paradox. Why the atmosphere is hotter than the surface. Why is the sun's atmosphere hundreds of times hotter than its surface? This violates our basic intuition about how heat works. When you move away from a heat source, it should get cooler. But the solar corona, the sun's outer atmosphere, reaches millions of degrees, while the surface below it is only 5,500 degrees. This problem, called the coronal heating paradox, has puzzled scientists for over 70 years. It was first noticed in the 1940s when astronomers measured temperatures of different solar atmosphere layers during eclipses. The data showed something impossible. Temperature increased as you moved away from the heat source. The sun's visible surface, the photosphere, is about 5,500 degrees Celsius. Moving outward, you encounter the chromosphere, which is somewhat hotter at 20,000 degrees. Then, abruptly, in the transition region, temperature jumps to over 1 million degrees. The outer corona can reach 2 to 3 million degrees during quiet periods and up to 10 million degrees during eruptions. This shouldn't be possible through normal heat conduction. Heat naturally flows from hot regions to cold, not the other way around. Something must be transporting or generating energy in the corona, heating it to extreme temperatures despite being far from the sun's energy source. Several theories compete to explain this paradox. The first involves magnetic reconnection. The sun's magnetic field is constantly twisting, breaking, and reconnecting. When magnetic field lines reconnect, they release tremendous energy. This energy heats the surrounding plasma to extreme temperatures. Observational evidence supports this idea. High-resolution images show magnetic reconnection events occurring constantly throughout the corona. Small flashes of brightness, each releasing energy equivalent to millions of nuclear bombs, appear and disappear. These microflares and nanoflares may provide the necessary heating. The second theory involves waves. The sun constantly generates waves through its convective motions. The sun's surface boils like water in a pot, with enormous convection cells bringing heat from the interior. This turbulent motion generates waves that propagate upward into the atmosphere. As these waves rise into regions of decreasing density, they increase in amplitude. Eventually, they become so strong they break, similar to ocean waves breaking on a beach. When they break, they dissipate their energy as heat, warming the plasma to millions of degrees. Several wave types can contribute: acoustic waves, sound, Alfvén waves, magnetic waves, and magnetoacoustic waves have all been detected in the solar atmosphere. Each type carries energy in different ways and dissipates that energy at different heights. Together, they may provide heating distributed throughout the corona. Recent observations from the Parker Solar Probe, which flies through the solar corona, detected direct evidence of Alfvén waves. The spacecraft measured sudden magnetic field reversals, called switchbacks, which are signatures of Alfvén waves. These waves carry substantial energy and are present throughout the corona. A third possibility involves electrical currents. The corona isn't perfectly electrically neutral. Small charge separations create electric fields. When electrons flow through these fields, they constitute electrical currents. These currents, flowing through resistive plasma, generate heat through the same process that heats wires and toasters. Likely, all these mechanisms contribute. Coronal heating may not have a single cause, but result from a combination of magnetic reconnection, wave dissipation, and current heating. The relative contribution of each mechanism may vary in different parts of the corona and at different times. The paradox becomes even more intriguing when you consider that the corona is continuously losing energy. The solar wind carries hot plasma away from the sun. Radiation radiates energy away. Yet despite these continuous losses, the corona remains millions of degrees hot. The heating mechanism must continuously replenish the lost energy. Calculating how much heating is needed reveals the problem's magnitude. The corona requires about 300 watts of heating per square meter to maintain its temperature against radiative losses and solar wind. This may not sound like much, but multiplied by the sun's surface area, it totals about 1026 watts, 100,000 times Earth's total received solar luminosity. Solving the coronal heating paradox has implications beyond understanding the sun. Sun-like stars throughout the galaxy likely have hot corona. Understanding how they work helps us understand stellar processes in general. Additionally, coronal heating drives the solar wind, which affects the entire solar system, including Earth. Recent missions are finally providing data to solve this decades-old mystery. The Parker Solar Probe flies through the corona, measuring conditions in situ. The Solar Orbiter observes from different angles. Together, these observatories are collecting the information needed to finally explain why the Sun's atmosphere defies expectations and burns millions of degrees hotter than the surface below. 15. Saturn develops electrical storms. When it receives solar bursts, did you know that storms billions of kilometers away can trigger lightning on Saturn? When solar wind bursts hit Saturn, something remarkable happens deep in its atmosphere. Massive electrical storms intensify, creating lightning thousands of times more powerful than anything on Earth. Saturn has a violent weather system. Lightning storms occur regularly in the deep clouds, where liquid water and ice interact. These storms produce electrical discharges detectable at 1.4 billion kilometers away. The Cassini probe recorded radio emissions from these storms that lasted weeks or even months. But something curious appeared in the data. The intensity and frequency of these storms correlate with solar activity. When the Sun launches a large coronal mass ejection that eventually reaches Saturn days later, electrical storms on Saturn intensify. Lightning becomes more frequent and more powerful. How can a solar storm affect deep weather on Saturn? The connection passes through the planet's magnetosphere. When energetic particles from the solar wind penetrate Saturn's magnetosphere, they create disturbances. These disturbances alter the electrical environment around the planet, including in the upper atmospheric layers. Saturn has an ionosphere, a region where solar radiation ionizes gas atoms, creating an electrically conductive layer. When solar storms increase the flux of energetic particles, the ionosphere responds. Electrical conductivity changes, electric fields adjust. These changes can propagate downward into the atmosphere. Models suggest that ionospheric changes can affect Saturn's global electrical circuit. Planets with atmospheres essentially have giant electrical circuit systems, with currents flowing between atmospheric layers. When the ionosphere changes due to solar activity, the entire circuit adjusts, potentially affecting storms deep in the atmosphere. Cassini observations showed that some of Saturn's largest storms occurred during periods of high solar activity. The Great White Storm of 2010 to 2011, a storm so large it encircled the entire planet, began during a period of increased solar activity. While correlation doesn't prove causation, it suggests a possible connection. Saturn's lightning is extraordinary on its own. Individual discharges release about 1 million times more energy than typical terrestrial lightning. The flashes are so bright they can be seen through Saturn's thick cloud layers. Cassini detected radio emissions at frequencies corresponding to about 10 discharges per second during active storms. Saturn's atmospheric structure contributes to these powerful storms. Water clouds exist about 100 kilometers below the visible cloud layers. In this region, liquid water and ice crystals coexist. Friction between particles, driven by strong updrafts, separates electrical charges, exactly as in terrestrial storms, but on a much larger scale. When solar bursts intensify these storms, the consequences are detectable throughout Saturn's atmosphere. The storms create vortices that can last months. They inject heat and moisture into upper layers. They create visible features that appear as bright spots in Saturn images. The Sun-Saturn connection reveals that weather on giant planets isn't isolated from external influences. Even at 1.4 billion kilometers from the Sun, where sunlight is 100 times weaker than on Earth, solar influence still penetrates. Energetic particles from the Sun travel this vast distance and still carry enough energy to affect planetary weather systems. Long-term cycles also appear. During the 11-year solar cycle, Saturn experiences variations in the amount of radiation and particles it receives. During solar maximum, more coronal mass ejections mean more magnetospheric disturbances. During solar minimum, conditions are calmer. This long-term modulation may influence weather patterns on Saturn on timescales of years to decades. Saturn's rings add another layer of complexity. Energetic particles interacting with the rings can create secondary electrons that then enter the atmosphere. These electrons can contribute to ionization and affect electrical conductivity. The rings essentially act as intermediaries between the solar wind and the atmosphere. Similar phenomena may occur on Jupiter, Uranus, and Neptune, but are harder to detect. Jupiter has powerful storms, but its extremely strong magnetosphere may shield it more from direct solar influence. Uranus and Neptune are so distant that detailed storm observations are rare. The fact that Saturn develops more intense storms during increased solar activity demonstrates interconnection on solar system scales. An eruption on the Sun's surface sends particles through over 1 billion kilometers of space. These particles interact with a giant planet's magnetosphere. That interaction alters the ionosphere. And finally, deep layers within the clouds respond with intensified lightning. It's a chain of causality that spans the solar system. 16. The sun's sound waves that never reach us. The sun is constantly screaming, but we never hear a sound. Inside the sun, gigantic infrasonic sound waves continuously reverberate, making the entire star vibrate like a giant bell. These waves carry information about the sun's deep interior, but they die before reaching space because sound cannot travel in vacuum. Imagine an organ the size of a star playing notes so low they take 5 minutes to complete a single cycle. These are the dominant acoustic waves in the sun. The sun's surface pulses up and down with amplitudes of several kilometers, moving in complex patterns created by the interference of millions of different sound waves. These waves are generated in the sun's convection zone, the outer region where heat is transported by turbulent plasma motions. Convection cells the size of entire states rise and sink, creating turbulence that generates acoustic waves. It's like having millions of speakers playing simultaneously inside a 1.4 million kilometer diameter sphere of gas. Sound waves travel through the sun's interior, reflecting and refracting in layers of different density. Some waves penetrate deep, almost to the core, before curving back to the surface. Other waves stay trapped in shallow layers. Each wave travels through regions with different temperatures, densities, and compositions, and its speed changes accordingly. When these waves return to the surface, they create interference patterns. Certain frequencies resonate, creating standing waves that make the entire surface oscillate in organized patterns. Astronomers have detected millions of these resonant frequencies, each corresponding to a different vibration mode. This field of study, called helioseismology, allows scientists to see inside the sun. Just as geologists use seismic waves from earthquakes to map Earth's interior, helioseismologists use solar sound waves to map the sun's interior. Different frequencies penetrate to different depths, providing information about temperature, density, composition, and rotation at each layer. The most common frequencies have periods of about 5 minutes. This means the sun's surface rises and falls every 5 minutes in certain locations. The motion is small, just a few kilometers, but on a star 1.4 million kilometers in diameter, it's detectable. Specialized instruments measure these oscillations by tracking how sunlight changes as material moves toward or away from us. But why do we never hear these waves? The answer is that sound requires a medium to travel through. Sound waves are compressions and rarefactions in a material, whether air, water, or plasma. In the vacuum of space, there's nothing to compress. When sound waves reach the sun's surface and try to continue outward, they simply stop. The energy dissipates in other ways, but the sound itself cannot propagate. If you could somehow place your ear on the sun's surface without instantly vaporizing, you'd hear a deafening roar. Millions of frequencies playing simultaneously would create a sound louder than anything possible on Earth. The sound pressure would be so intense it would destroy any material structure. Scientists have managed to convert solar frequencies into audible sound by speeding them up. The 5-minute oscillations, when accelerated 42,000 times, become audible to human ears. The result sounds like a low, vibrating hum, almost as if the sun were snoring or buzzing. Different regions of the sun produce slightly different frequencies, creating a complex chorus. Sound waves revealed surprising secrets about the sun. They showed that the sun's core rotates faster than the surface, completing one rotation every 7 days compared to 25 days at the surface equator. They mapped jet streams below the surface, plasma flows similar to jet streams in Earth's atmosphere, but much more powerful. Sound waves also detected changes in the sun's interior throughout the solar cycle. As sunspots appear and disappear, subtle changes in sound wave velocities reveal changes in the magnetic field and temperature below the surface. This provides early warnings of imminent solar activity. During solar eclipses, when the moon blocks light from the sun's surface, sound waves continue unchanged. This confirms they originate in the interior, not at the surface. The sun continues vibrating at the same rhythm regardless of whether we're observing or not. The convection zone isn't the only source of sound waves. Sudden explosions like solar flares also generate acoustic waves. These waves travel inward, plunging into the solar interior before reflecting back. By tracking them, scientists can locate where the explosion occurred and how much energy was released. Some sound waves get trapped in specific layers, creating acoustic waveguides. These waves can travel horizontally for large distances below the surface before emerging at a different location. They create patterns that appear as expanding rings on the surface, similar to ripples in a pond after a stone is thrown. The sun isn't unique in this. All stars vibrate with internal sound waves. Asteroseismology, the study of stellar oscillations, applies the same techniques to other stars. Space telescopes like Kepler detected oscillations in thousands of stars, allowing scientists to determine their masses, sizes, ages, and internal compositions. The silence of space hides a symphony. The sun plays continuously, vibrating with frequencies containing information about its internal structure and processes. These waves never reach us as sound, but by measuring their effects on the solar surface, we can hear the secrets the sun's interior has to tell. 17. Solar tsunamis. Moving at 720,000 kilometers per hour. Imagine a wave so large it could swallow the entire Earth, moving so fast it crosses the Earth-Moon distance in less than half an hour. Solar tsunamis are giant shock waves that sweep across the sun's surface after powerful eruptions traveling at velocities that seem to defy physics. These waves, officially called Morton waves or EIT waves, named after the instrument that discovered them, were first observed in 1960. They appear as bright, expanding rings propagating through the solar chromosphere after a flare. In extreme ultraviolet light images, they appear as circular wavefronts moving outward from the eruption site. A typical solar tsunami begins when a solar eruption releases tremendous energy. This sudden release creates a shock wave that propagates through the solar atmosphere. Think of it as an underwater explosion creating an ocean tsunami, but on a scale millions of times larger and in superheated plasma instead of water. These waves' speed is stunning. Observations measured solar tsunamis moving at velocities of 200 to 400 kilometers per second, with some extreme cases exceeding 2,200 kilometers per second. To put this in perspective, 400 kilometers per second is 1.44 million kilometers per hour, about 0.13% the speed of light. At this speed, a solar tsunami would cross Earth's diameter in less than 30 seconds. It could travel from Earth to the Sun in about 10 hours. Compared to terrestrial ocean tsunamis, which move at about 800 kilometers per hour, solar tsunamis are about 1,000 times faster. What drives these extreme speeds? The answer lies in the solar plasma's properties. Sound speed in plasma depends on temperature. The solar chromosphere, where these waves travel, has temperatures of tens of thousands of degrees. At these temperatures, sound waves and shock waves can travel much faster than in cooler gases. But solar tsunamis aren't just sound waves. They're magnetohydrodynamic waves, meaning they involve interactions between plasma, magnetic fields, and pressure. The sun's magnetic field provides additional structure that can guide and accelerate these waves. In some regions, waves can travel along magnetic field lines, reaching even higher velocities. A solar tsunami's wavefront isn't subtle. It compresses plasma as it passes, temporarily increasing density and temperature. This compression causes plasma to emit brighter light, making the wave visible in ultraviolet light images. The wave appears as a bright edge moving across the solar surface. Detailed observations revealed surprising complexity. Solar tsunamis aren't always circular and symmetric. They can be distorted by existing magnetic structures on the solar surface. Strong magnetic fields can slow or redirect waves. Some waves break or reflect when encountering magnetic barriers. NASA's Solar Dynamics Observatory captured spectacular videos of solar tsunamis. One particularly dramatic event in 2011 showed a wave sweeping across about half the visible solar surface. The wave traveled over 700,000 kilometers in about an hour, maintaining a speed of nearly 400 kilometers per second throughout. Solar tsunamis can trigger secondary eruptions. When the shock wave passes over a region with unstable magnetic fields, the compression can destabilize those fields. The result can be additional flares or coronal mass ejections launched from sites distant from the original eruption. It's a domino effect where one explosion triggers others across the sun's surface. The energy carried by these waves is colossal. A single solar tsunami wave can transport about 1 septillion joules of energy, equivalent to about 100 million hydrogen bombs. Most of this energy eventually dissipates as the wave travels, heating the surrounding plasma. Studying solar tsunamis provides insights into the solar atmosphere's structure. The speed at which waves travel depends on the plasma properties they traverse. By measuring wave speeds in different regions, scientists can map temperature, density, and magnetic field strength throughout the chromosphere and corona. Solar tsunamis also serve as warnings. When a major eruption launches a solar tsunami across the surface, a coronal mass ejection was likely launched into space as well. Observing the wave on the surface provides information about the eruption's energy and direction, helping predict whether Earth will be affected. Comparisons with terrestrial tsunamis reveal intriguing similarities despite the vast differences in scale and medium. Both are shock waves propagating through a fluid. Both can travel great distances. Both can trigger secondary effects in distant regions. But where terrestrial tsunamis take hours to cross oceans, solar tsunamis cross similar distances in minutes. Every major solar eruption creates these giant waves. They sweep across the surface, carrying information about the explosion that created them. Traveling at a significant fraction of light speed, they demonstrate that the sun's surface is a place of constant motion and energy, where phenomena operate on scales of velocity and power we rarely encounter in human experience. 18. The Carrington Event. When the sun set, telegraphs on fire. On the morning of September 1, 1859, telegraphs throughout Europe and North America began behaving strangely. Sparks flew from the equipment, operators received electrical shocks, some paper caught fire. Bright auroras, normally confined to polar regions, appeared as far south as the Caribbean. The sun had launched the most powerful geomagnetic storm ever recorded. The event began 2 days earlier, on August 28, 1859. British astronomer Richard Carrington was observing sunspots through his telescope when he saw something extraordinary. 2 bright arcs of light suddenly appeared over a sunspot group, rapidly intensifying and then disappearing within 5 minutes. Carrington had witnessed the first solar flare observed by humans. 17 hours later, on the night of September 1st, chaos began. Auroras appeared as far south as Cuba, Hawaii, and Rome. People in the northeastern United States could read newspapers at midnight under auroral light. Miners in the Rocky Mountains woke up thinking it was morning and began preparing breakfast, only to realize it was still night. But telegraphs suffered the most dramatic effects. The telegraph system, then the most advanced communication technology, spanned thousands of kilometers of wires across Europe and North America. These long wires acted as giant antennas, picking up electrical currents induced by Earth's rapidly changing magnetic field. Telegraph operators in Boston reported that currents so strong flowed through their equipment they could disconnect the batteries and operate solely on electricity induced by the geomagnetic storm. In some locations, paper used to record messages caught fire due to intense sparks. Operators received shocks when touching their equipment. What caused this devastation? Carrington had observed an extremely powerful coronal mass ejection. A cloud containing billions of tons of plasma was launched from the sun directly toward Earth. Traveling at an exceptional speed of about 2,500 kilometers per second, it crossed the 150 million kilometers in less than 18 hours, much faster than the typical 3 to 4 day transit time. When this magnetized plasma cloud hit Earth's magnetic field, it compressed it violently. The magnetosphere, normally extending 60,000 kilometers on the sun side, may have been compressed to half that distance. The sudden compression and dramatic magnetic changes induced electrical currents in the ground and in any long conductors. These geomagnetically induced currents flowed through the ground and found telegraph wires, which offered a path of lower resistance. The currents, measuring hundreds of amperes in some cases, were far larger than the few amperes telegraph systems were designed to handle. The result was overheating, sparks, and equipment damage. The geomagnetic storm was so intense it created what scientists call a DIST index of about 1,960 NT, a measure of geomagnetic measure of disturbance. For comparison, severe modern geomagnetic storms typically reach 200 to 300 NT. The Carrington event was 5 to 8 times more powerful than any storm in the last 150 years. If a Carrington event occurred today, the consequences would be catastrophic. Our civilization depends on electrical grids, satellites, GPS, and electronics, all vulnerable to extreme geomagnetic storms. Transformers and power grids could overheat and melt. Satellites could be damaged by radiation. GPS systems could fail due to ionospheric disturbances. Studies estimate that a Carrington-level event today would cause $1 to $2 trillion in damage to the United States alone. Large portions of electrical grids could fail for weeks to months. Communication satellites could be permanently damaged. The total economic cost could exceed several $1 trillion globally. Historical evidence suggests Carrington-level events aren't as rare as we'd like to think. Ice core analyses show peaks in radioactive isotopes produced by intense solar particles. Events comparable to or larger than Carrington may have occurred in 774 CE, 993 CE, and possibly other times in history. A near-miss event in July 2012 provides a worrying reminder. An extremely powerful coronal mass ejection, potentially as strong as the Carrington event, was launched from the Sun. Fortunately, it was directed away from Earth, passing through Earth's orbit about a week before we were there. The Stereo A spacecraft traversed the storm and measured its properties, confirming its intensity. Today, we have warning systems that didn't exist in 1859. Satellites monitor the Sun continuously. When a major flare erupts, we receive warning within minutes. When a coronal mass ejection is launched, we can estimate its velocity and direction. This provides perhaps 12 to 36 hours of warning before arrival, enough time to take protective measures. The Carrington event's auroras were described in hundreds of eyewitness accounts. People reported blood-red auroras, undulating green curtains, and bright rays. Some reported hearing strange sounds during the displays, possibly related to electrical discharges in the air. The intensity was so great that people were genuinely frightened, fearing the end of the world. The event proved that the Sun could affect Earth in powerful and unpredictable ways. Before 1859, the connection between the Sun and terrestrial phenomena was just speculation. After Carrington, it became clear we live in a connected solar system where solar explosions can have real consequences for human technology and society. Each time the Sun enters an active period, scientists monitor carefully, knowing that another Carrington event is inevitable eventually. The question isn't whether it will happen, but when. And when it does, our technological civilization will face a test unlike any other in modern history. 19 spicules, 10,000-degree jets shooting into space. Every second at the Sun's edge, an invisible forest is constantly growing and dying. Tens of thousands of plasma jets, each 10,000 kilometers tall and heated to 10,000 degrees Celsius, shoot upward every second. These are spicules. Phenomena so common on the solar surface that hundreds of thousands exist at any moment, but so fast and small they've been mysterious for over a century. Spicules appear as thin blades of plasma shooting from the solar chromosphere into the corona. Imagine grass growing at supersonic speeds, with each blade reaching heights of 10,000 kilometers in just 5 to 10 minutes. That's what spicules look like in high-resolution images of the solar edge. Each individual spicule is about 300 kilometers wide, approximately the distance between New York and Boston, but they rise to heights of 10,000 kilometers, giving them an aspect ratio of about 30.1, making them incredibly thin and elongated. It's like having plasma needles shooting out from the Sun's surface. The velocity is stunning. Spicules move upward at 50 to 150 kilometers per second. That's 180,000 to 540,000 kilometers per hour. At this speed, a spicule could travel from Earth's surface to space in less than 1 second. They accelerate from zero to these tremendous velocities in just a few seconds. But as quickly as they appear, they disappear. Most spicules last only 5 to 10 minutes. They shoot upward, reach their maximum height, and then either fall back or disappear as the plasma heats up and mixes with the surrounding corona. At every moment, old spicules are disappearing while new ones are forming. The total count is staggering. An estimated 10 million spicules exist on the Sun's surface at any moment. With each lasting about 5 to 10 minutes, this means hundreds of thousands of new spicules form every second. The Sun's entire surface is constantly ejecting these plasma jets. What causes spicules? For decades, their origin was a mystery. Recent high-resolution observations provided answers. Spicules are driven by magnetoacoustic shock waves. Convective motions just below the solar surface generate waves that travel upward. When these waves hit the chromosphere, they develop into shocks that launch plasma upward along magnetic field lines. The magnetic field plays a crucial role. Spicules follow magnetic field lines like trains follow tracks. Magnetic fields channel and guide the upward-moving plasma, giving spicules their characteristic elongated shape. Where magnetic field lines are more vertical, spicules shoot straight up. Where fields are inclined, spicules follow corresponding angles. There are actually two types of spicules. Type Y spicules are slower and last about 5 to 10 minutes. Type 2 spicules are faster, hotter, and last only 3 to 7 minutes. Type 2 spicules move at velocities up to 150 kilometers per second and can transport plasma, heated to 100,000 degrees or more, into the corona. These Type 2 spicules may be important for coronal heating. They inject hot plasma from the chromosphere into the corona at a tremendous rate. Calculations suggest spicules provide enough mass to replenish all coronal plasma every few hours. They also transport energy, possibly contributing to maintaining the corona at millions of degrees. High-resolution observations revealed that spicules aren't smooth. They have complex internal structure, often consisting of multiple intertwined filaments. They twist and bend as they rise, responding to the changing magnetic field. Some split into multiple jets, others merge as they rise. The Swedish Solar Telescope and Solar Dynamics Observatory captured mesmerizing videos of spicules. The images show the sun's edge looking like an undulating forest, with thousands of jets shooting upward and falling back. The effect is almost biological, as if the sun were covered with tentacles constantly reaching into space. Spicules also appear in other parts of the solar surface, not just at the edge. Viewed from above, they appear as dark, rosette-shaped features around magnetic field concentrations. These features, called rosettes, are actually spicules seen from above rather than from the side. The total mass transported by spicules is substantial. Spicules are estimated to move about 100 times more mass into the corona than is lost through the solar wind. Most of this material eventually falls back, but some escapes, feeding the solar wind and coronal mass ejections. Spicules' temperature is intriguing. They start in the chromosphere at about 10,000 degrees Celsius. As they rise, some cool through radiation. But Type 2 spicules somehow heat up as they rise, reaching 100,000 degrees or more. This heating suggests additional energy is being deposited in the plasma, possibly through magnetic reconnection or wave dissipation. Observing spicules requires specialized instruments. They're much smaller and faster than solar features older telescopes could resolve. Only in the last 2 decades, with the advent of high-resolution solar telescopes in space and on the ground, have scientists been able to study spicules in detail. Each spicule is an experiment in plasma physics, showing how shock waves, magnetic fields, and gravity interact. Together, the millions of spicules covering the sun create a dynamic and turbulent interface between the solar surface and corona. They demonstrate that the boundary between the sun and space isn't a sharp surface, but a region of constant flux where plasma shoots upward and falls back in an endless cycle. 20. Venus loses ton of oxygen per second to the solar wind. Venus is bleeding oxygen. Every second, the planet loses about 1 ton of oxygen stripped from its upper atmosphere by the relentless solar wind. Over billions of years, this process has stripped Venus of vast amounts of water, transforming what may have been an ocean world into a parched inferno. Venus's atmosphere is 96% carbon dioxide, with only traces of other gases. But in the distant past, Venus may have had significant water, possibly even oceans. Where did all that water go? The answer lies above, in the upper atmosphere, where the solar wind is currently removing the breakdown products of that lost water. When water molecules in the upper atmosphere are exposed to solar ultraviolet radiation, they break apart through a process called photolysis. Radiation splits H2O into hydrogen and oxygen. Hydrogen, being extremely light, escapes Venus's gravity easily. Oxygen, heavier, should theoretically remain, but it doesn't remain. The solar wind interacts with Venus's upper atmosphere in complex ways. Venus has no significant intrinsic magnetic field, so it lacks a protective magnetosphere like Earth's. The solar wind hits the upper atmosphere, called the ionosphere, directly where solar radiation has created a region of ionized atoms. The interaction creates what's called an induced magnetosphere. The magnetic field embedded in the solar wind drapes around Venus, creating a temporary magnetic structure. But this protection is imperfect. Oxygen ions in the ionosphere can escape along magnetic field lines, being swept away by the solar wind. Observations from ESA's Venus Express probe, which orbited Venus from 2006 to 2014, measured this loss. Instruments detected oxygen ions flowing away from Venus in two main streams. One stream flows over the poles, where magnetic field lines provide an escape path. Another flows from one side, dragged by the solar wind. The loss rate varies with solar activity. During quiet periods, Venus loses about 500 to 700 kilograms of oxygen per second. During solar storms, when the solar wind is stronger and faster, the rate increases to 1 ton or more per second. The sudden increase happens because the stronger solar wind compresses the ionosphere, allowing more ions to escape. 1 ton per second might sound like a lot, but on geological scales, it's devastating. Over 1 billion years, this totals about 3 times 10 to the 16 kilograms of oxygen. To put this in perspective, this amount of oxygen, if originally part of water molecules, would represent a global ocean about 3 meters deep covering Venus. But the loss has been greater in the past. When the sun was young, it was more active, producing stronger solar wind and more intense ultraviolet radiation. Venus's atmospheric escape rate may have been 10 to 100 times higher in the first billions of years of the solar system. This means tremendous amounts of water could have been lost. Through this process, hydrogen loss was even more dramatic. Hydrogen escapes more easily than oxygen due to its lower mass. For every oxygen atom lost, 2 hydrogen atoms escaped, maintaining the original H2O proportions. But because hydrogen is much lighter, the mass loss was dominated by oxygen. Venus isn't alone in this atmospheric loss. Mars suffered a similar fate, losing much of its atmosphere to the solar wind after its global magnetic field failed billions of years ago. The difference is that Venus is larger and has stronger gravity, so it retained its dense carbon dioxide atmosphere even while losing water. The question of how much water Venus originally had remains debated. Measurements of the deuterium to hydrogen ratio in Venus's current atmosphere provide clues. Deuterium, a heavier form of hydrogen, escapes more slowly. The elevated deuterium to hydrogen ratio suggests substantial hydrogen was lost, consistent with Venus having had much more water in the past. Computer simulations modeled Venus's atmospheric evolution over billions of years. The models include solar radiation, solar wind, atmospheric escape, and chemical processes. They suggest Venus could have maintained liquid water for perhaps 1 billion years after its formation, before runaway greenhouse effect vaporized all oceans and atmospheric escape removed the vapor. The ongoing oxygen loss today is just the final stage of a catastrophe that unfolded over eons. The solar wind, acting relentlessly over billions of years, transformed Venus. What may have been a habitable world with oceans became a scorching desert with thick carbon dioxide atmosphere and surface temperatures of 465 degrees Celsius. Understanding this process has implications for exoplanets. Many Earth-like planets orbit close to their stars, where radiation and stellar wind are intense. These planets may suffer accelerated atmospheric escape. If they lack protective magnetic fields, they may lose their atmospheres rapidly on geological timescales. Venus serves as a cautionary tale. It shows that being in the habitable zone doesn't guarantee habitability. It shows that greenhouse effects can spiral out of control. And it shows that without a protective magnetic field, an atmosphere can be gradually stripped away, atom by the sun's relentless wind. The ton of oxygen Venus loses every second represents the final chapter in a billions of years story of planetary transformation. 21. Magnetic field lines that break and reconnect. What happens when you twist a rubber band until it snaps? On the sun, something similar happens with magnetic field lines, but the energy release is equivalent to billions of nuclear bombs. Magnetic reconnection is one of the most violent and energetic processes in the solar system, transforming stored magnetic energy into heat, motion, and radiation in fractions of a second. Magnetic field lines on the sun aren't physical objects. They're mathematical representations of how the magnetic field is oriented in space. But solar plasma is so strongly coupled to the magnetic field that these lines freeze into the plasma. When plasma moves, field lines go along. When field lines twist, they store energy. The sun constantly twists its magnetic field. Turbulent convective motions below the surface drag magnetic fields around, coiling and twisting them. Differential rotation, where the equator rotates faster than the poles, winds field lines like spaghetti being wound on a fork. Over time, magnetic energy accumulates. Eventually, something has to give. When oppositely directed magnetic field lines are forced close together, they can undergo reconnection. The magnetic field topology changes abruptly. Lines that were connecting two regions suddenly break and reconnect with different partners. This rearrangement releases stored energy explosively. The amount of energy released can be staggering. A single typical magnetic reconnection event releases about 10 to 125 joules of energy. That's equivalent to 1 billion megaton hydrogen bombs. Larger events can release 10 to 100 times more energy. This energy is released within minutes, creating one of the most intense energy release rates in nature. Where does all this energy go? Part goes into heating surrounding plasma to millions of degrees. Part goes into accelerating particles to relativistic speeds close to the speed of light. Part goes into bulk kinetic energy, launching billions of tons of plasma into space in coronal mass ejections. And part is radiated as light, X-rays, and even gamma rays. Magnetic reconnection is responsible for solar flares. When you see a bright explosion on the sun's surface in ultraviolet or X-ray images, you're witnessing magnetic reconnection in action. The reconnection region appears as a bright point where superheated plasma at millions of degrees emits intense radiation. The process also creates impressive structures. After reconnection, newly connected magnetic field lines often form arcs or loops. Hot plasma gets trapped in these loops, flowing along them and creating the bright arch-shaped features seen in solar images. Some of these loops extend hundreds of thousands of kilometers above the solar surface. Magnetic reconnection isn't exclusive to the sun. It happens in Earth's magnetosphere, especially in the magnetotail, where Earth's magnetic field extends on the night side. When the solar wind compresses the magnetosphere, it stretches magnetic field lines in the tail. Eventually, these lines reconnect, releasing energy that powers auroras and geomagnetic storms. The basic physics of reconnection was a mystery for decades. The problem was speed. Calculations using normal electrical conductivity of plasma predicted reconnection should be extremely slow, taking hours or days. But observations showed reconnection happening in minutes. Something was dramatically accelerating the process. The answer involves turbulence and small-scale structures. The reconnection region isn't smooth and orderly. It's turbulent and full of complex magnetic structures at small scales. This turbulence allows reconnection to occur much faster than simple theories predicted. Magnetic instabilities create islands and filaments that facilitate field rearrangement. Recent space missions provided unprecedented direct observations. NASA's Magnetospheric Multiscale Mission uses 4 spacecraft flying in precise formation through reconnection regions in Earth's magnetosphere. Instruments measure magnetic fields, electric fields, and particle distributions with millisecond temporal resolution and kilometer spatial resolution. The data revealed the reconnection region structure in stunning detail. At the center is a diffusion region where field lines actually break and reconnect. This region is only tens of kilometers wide in Earth's magnetosphere, probably tens to hundreds of kilometers on the sun. Within it, the magnetic field changes direction drastically over short distances. Electrons and ions behave differently during reconnection. Electrons, being light, react instantly to magnetic field changes. Ions, being heavier, respond more slowly. This temporary charge separation creates electric fields that accelerate particles to tremendous energies. Some electrons are accelerated to 10% the speed of light or more. Magnetic reconnection also occurs in other parts of the solar system. In Jupiter's and Saturn's magnetospheres, Reconnection releases stored energy, contributing to powerful auroras. In comet tails, where the solar wind interacts with comet material, reconnection can slice off entire chunks of tail, which then drift away as disconnected clouds. Stars beyond the Sun also exhibit magnetic reconnection. Giant stellar flares, some thousands of times more powerful than the largest solar flares, have been observed on other stars. These superflares likely result from magnetic reconnection events on even larger scales than the Sun's, releasing enough energy to affect the habitability of any nearby planets. Each time the Sun's magnetic field becomes too twisted, reconnection provides a relief valve. Stored energy is released explosively, resetting the field configuration to something simpler. But the turbulent convective motions continue, immediately beginning to build magnetic tension again. It's an endless cycle of energy, storage, and release, powering the solar activity. We observe 22 coronal mass ejections, clouds of billions of tons, launched into space. Imagine the Sun hurling a bubble of magnetized plasma containing more mass than Mount Everest into space at millions of kilometers per hour. This happens regularly. Coronal mass ejections, or CMEs, are the largest and most dramatic solar eruptions, launching billions of tons of material in giant clouds that can engulf entire planets. A typical CME contains about 1 to 10 billion tons of plasma. That's approximately the mass of all water in Lake Superior, or thousands of times the mass of a large mountain. This tremendous mass is ejected from the solar corona and accelerated to velocities of 300 to 3,000 kilometers per second, depending on the eruption's strength. The fastest CMEs can cross the 150 million kilometers from Earth to the Sun in just 14 to 18 hours. Slower CMEs take 3 to 4 days. When they reach Earth, these massive clouds collide with our planet's magnetic field, triggering geomagnetic storms that can disrupt satellites, power grids, and communications. What causes these giant eruptions? CMEs are driven by instabilities in the solar magnetic field. Regions of the corona can develop magnetic structures that become so twisted and energy-loaded they become unstable. When instability reaches a critical point, the entire structure erupts outward, carrying plasma and embedded magnetic field with it. Observations show that CMEs often originate from solar prominences. A prominence is a large structure of denser, cooler plasma suspended above the solar surface by magnetic fields. Prominences can remain stable for days or weeks, but if the underlying magnetic structure becomes unstable, the entire prominence can be launched into space as a CME. CME shapes are spectacular. Coronagraph images, instruments that block bright light from the solar surface to reveal the faint corona, show CMEs as halo-shaped or bubble-like structures expanding away from the Sun. Many have a three-part structure: a bright frontal arc, a dark cavity, and a bright core that is the prominence material being ejected. The energy released in a large CME is colossal. A typical CME carries about 1024 to 1025 joules of kinetic energy, equivalent to hundreds of millions to billions of hydrogen bombs. The largest CMEs can release up to 10,026 joules or more. Part of this energy is in bulk motion, part in magnetic energy embedded in the plasma. CMEs aren't rare. During solar maximum, when the Sun is at its most active point in the 11-year cycle, the Sun can launch 3 to 5 CMEs per day. During solar minimum, the rate drops to perhaps 1 every few days. Over a complete solar cycle, the Sun produces several thousand CMEs. Most CMEs don't hit Earth. The Sun ejects CMEs in all directions. Earth is a small target in vast space. Statistically, only about 5% of CMEs are directed toward Earth, but those that hit can have significant effects. When a CME hits Earth's magnetosphere, the interaction depends crucially on the orientation of the magnetic field embedded in the CME. If the CME's magnetic field is oriented southward, opposite to Earth's field, magnetic reconnection occurs efficiently. This allows energy from the CME to be transferred to Earth's magnetosphere, triggering intense geomagnetic storms. The resulting geomagnetic storm can be dramatic. Auroras appear at much lower latitudes than normal. Induced currents flow in the ground and power lines. Satellites may experience anomalies or damage due to increased radiation. GPS signals can be degraded. Power grid operators must take measures to protect transformers. The fastest CME ever recorded occurred in August 1972, reaching Earth in just 14.6 hours after leaving the Sun. This implies an average speed of about 2,150 kilometers per second. Fortunately, this CME hit between Apollo missions, so no astronauts were in space. If astronauts had been on the Moon, they would have received dangerous radiation doses. Beyond speed and mass, CMEs carry strong magnetic fields. The embedded magnetic field can have intensities of 20 to 100 nanoteslas when it reaches Earth's orbit, hundreds of times stronger than the normal interplanetary magnetic field. This strong field is crucial for driving intense geomagnetic storms. CMEs also produce energetic particles. As the shock wave at the front of a CME propagates through space, it accelerates protons and other particles to very high energies. These solar energetic particles can reach Earth before the CME itself, creating radiation storms that are dangerous to astronauts and satellites. Studying CMEs requires a fleet of spacecraft. Solar observatories like SOHO and SDO observe the Sun continuously, detecting CMEs when they're launched. Spacecraft like ACE and DSCO-VR orbit between the Sun and Earth, providing last-minute warnings when a CME is about to arrive. And missions like STEREO provide views from different angles, allowing scientists to track CMEs in 3 dimensions. CME forecasting has improved dramatically in recent decades, but remains challenging. We can detect when a CME is launched and roughly estimate its direction and speed. But precisely predicting whether a CME will hit Earth, when it will arrive, and how strong the impact will be still involves significant uncertainties. Understanding CMEs is crucial for protecting our technological society. As we become more dependent on satellites, wireless communications, and interconnected electrical infrastructure, we become more vulnerable to space weather. CMEs represent the largest space weather threat, capable of disrupting global systems. Forecasting and mitigating their effects is a growing priority for scientists and policymakers. 23. The Sun's 11-year heartbeat. The Sun has a pulse. Every 11 years, solar activity rises and falls in a regular cycle that affects the entire solar system. Sunspots appear and disappear, flares and CMEs increase and decrease, and even the Sun's total brightness varies slightly. This solar cycle has been observed for centuries, but understanding why it happens has revealed deep secrets about the Sun's inner workings. The solar cycle is most easily tracked through sunspots. During solar minimum, the Sun may have no spots for days or weeks. The surface appears clean and calm. Then, as the cycle progresses, spots begin appearing at mid-latitudes, about 30 degrees north and south of the equator. The number of spots increases, and they appear increasingly closer to the equator. At solar maximum, the Sun is covered with spots. Dozens of sunspot groups may be visible simultaneously. Solar flares and CMEs occur frequently. The corona appears complex and structured, full of bright magnetic loops. The Sun is in its most active phase, releasing energy more violently and frequently. After maximum, activity declines. Spots become less numerous. They appear increasingly closer to the equator. Eventually, the cycle ends with the last spots appearing near the equator, and the Sun returns to solar minimum quietude. The entire cycle, from minimum to minimum, averages 11 years. Though individual cycles vary from 9 to 14 years. But there's more to this cycle than just spots. The Sun's magnetic field undergoes a complete transformation. At the beginning of a cycle, the Sun has a relatively simple dipolar magnetic field, like a bar magnet with a north pole and south pole. As the cycle progresses, the field becomes more complex with strong local fields in sunspot regions. At solar maximum, the global magnetic field becomes chaotic. Then something remarkable happens. The magnetic poles reverse. The magnetic north pole becomes the south pole, and vice versa. This reversal doesn't happen instantly, but over several months near solar maximum. It's as if the Sun resets its magnetic field every 11 years. But wait, there's more. If you track the magnetic polarity of sunspots, you discover that spots in the northern hemisphere have one polarity during one cycle and the opposite polarity during the next. The same holds for the southern hemisphere. This means it takes 2 11-year cycles, or 22 years, for the complete pattern to repeat. The Sun's full magnetic cycle is actually 22 years. What causes this cyclical behavior? The answer lies in a process called the solar dynamo, Turbulent convective motions and differential rotation in the sun's interior generate and amplify magnetic fields. Existing weak magnetic fields are stretched, twisted, and intensified by these motions, creating the strong fields observed in sunspots. Differential rotation is crucial. The sun's equator rotates faster than the poles, completing one rotation in about 25 days at the equator versus 35 days at the poles. This differential rotation takes magnetic fields that initially run north-south and winds them in the east-west direction. Over several years, fields are wound many times, intensifying them tremendously. Eventually, these intensified magnetic fields become buoyant and rise through the convection zone to the surface. Where they emerge, they suppress convection because strong magnetic field inhibits plasma motion, creating cooler regions that appear dark against the bright surrounding surface. These are sunspots. As more and more magnetic fields emerge and create complexity, the sun's global field becomes increasingly disorganized. Eventually, it reaches a point where the original dipolar field is completely obscured by the complex field created by all the sunspots. This corresponds to solar maximum. After maximum, new sunspot production declines. Existing magnetic fields gradually cancel out through reconnection and diffusion. The global dipolar field reasserts itself, but with opposite polarity. The cycle has begun again, but with magnetic poles reversed. Why is the period 11 years? That's a harder question. The period depends on the details of how convection, rotation, and magnetic fields interact in the solar interior. Computer models of the solar dynamo can reproduce 11-year-like cycles, but the details of why the sun chooses this particular period aren't fully understood yet. The solar cycle affects the entire solar system. The sun's total output varies about 0.1% between minimum and maximum, with the sun being slightly brighter at maximum despite having more dark spots. Ultraviolet radiation varies much more, up to 10% or more. The solar wind is faster and more variable during solar maximum. These cycles affect Earth. During solar maximum, more geomagnetic storms occur, creating more frequent auroras. Earth's ionosphere responds to changes in ultraviolet radiation, affecting radio propagation. There's even subtle evidence that the solar cycle affects weather patterns, though the mechanisms are complex and debated. Historical sunspot records go back to 1610, when Galileo first observed them through a telescope. These 400 years of data reveal that the cycle isn't perfectly regular. Some cycles are strong, with many spots and intense activity. Others are weak. Occasionally, the cycle almost stops completely. The most famous example is the Maunder minimum from 1645 to 1715, when sunspots virtually disappeared for 70 years. During this period, the sun appears to have entered a very low activity state. Interestingly, this period coincided with particularly cold conditions in Europe, part of the so-called Little Ice Age, though the causal connection remains uncertain. The current solar cycle, Solar Cycle 25, began in December 2019. It's predicted to reach maximum around 2025, though precise predictions are difficult. So far, it appears to be a moderate strength cycle, similar to the previous cycle. Understanding the solar cycle isn't just academically interesting, it's practically important for predicting space weather. Knowing whether we're approaching solar maximum or minimum helps forecast the likelihood of large solar storms. During maximum, vigilance increases. During minimum, we can relax somewhat, knowing major eruptions are less likely. The sun's 11-year heartbeat reminds us that our star isn't constant and unchanging. It's a dynamic object with its own internal rhythm, pulsing with magnetic activity that waxes and wanes over years and decades. And as long as this pulse continues, the entire solar system will dance to its rhythm. 24. Sunspots cooler than the surface, but still at 6,500 degrees. Why do the darkest parts of the sun actually glow with temperatures that would vaporize any known material? Sunspots appear as dark blemishes against the sun's bright surface, but that's just contrast. A typical sunspot is still at about 3,500 to 4,000 degrees Celsius, and the hotter regions around it reach 6,500 degrees or more, hot enough to melt any element. The sun's normal surface, the photosphere, has a temperature of about 5,500 degrees Celsius. At this temperature, it glows with intense white-yellow light. Sunspots are about 1,000 to 2,000 degrees cooler, typically around 3,500 to 4,000 degrees. This temperature difference may not seem enormous, but it has a dramatic effect on brightness. An object's brightness increases dramatically with temperature, following the Stefan Boltzmann law. A region that's 1/500 degrees cooler emits only about 1/3 the light. That's why sunspots appear dark. They're still emitting tremendous light, but compared to the even brighter surroundings, they seem dark. If you could isolate a sunspot against black space, it would shine more brilliantly than anything on Earth. A sunspot's light is brighter than a welding arc, brighter than molten metal, brighter than lava. But against the even brighter photosphere, it appears as a dark spot. What makes sunspots cooler? The answer is magnetic fields. Sunspots are regions where intense magnetic fields emerge from the sun's surface. These fields can be 1,000 to 4,000 times stronger than Earth's magnetic field, reaching intensities of 0.3 to 0.4 Tesla, comparable to powerful industrial magnets. Strong magnetic fields suppress convection. Normally, heat is transported from the sun's interior to the surface by convection, the bulk motion of hot plasma rising and cooler plasma sinking. But plasma is ionized, meaning it contains charged particles. Charged particles are strongly affected by magnetic fields. In regions with very strong magnetic fields, plasma cannot move freely up and down. The magnetic field inhibits convective motion. With convection suppressed, less heat is transported to the surface in these regions. The result is that the surface cools, creating the darker spot we observe. Sunspots have complex structure. The dark center is called the umbra. It's the coolest and darkest region, where the magnetic field is strongest and most vertical. Around the umbra is the penumbra, a region of radial light and dark filaments. The penumbra has more inclined magnetic fields and intermediate temperatures between the umbra and surrounding photosphere. The filaments in the penumbra are fascinating. They represent plasma flows moving outward from the spot at velocities of 5 to 10 kilometers per second. These flows, called Evershed flows, transport heat and angular momentum. They're part of the complex system of convection and magnetic flux around sunspots. Sunspots come in a variety of sizes. Small spots may be just a few thousand kilometers in diameter, smaller than Earth. Large spots can reach 50,000 kilometers or more, large enough to swallow several Earth-sized planets. The largest sunspot ever recorded in April 1947 had a diameter of about 330,000 kilometers, more than a quarter of the sun's diameter. Sunspots often appear in pairs or complex groups. That's because magnetic fields form loops. A magnetic field emerges at one location, creating a spot with north polarity, arcs through the corona, and plunges back down at another location, creating a spot with south polarity. These bipolar regions are the most common sunspot configurations. Sunspot lifetimes vary. Small spots may last only a few days before dissipating. Large spots can persist for weeks or even months, surviving multiple solar rotations. The longest-lived recorded sunspot persisted for about 200 days in 1943-1944, becoming visible every 27 days as the sun rotated. Sunspots are important because they mark regions of intense magnetic fields. These regions are where solar flares and CMEs are most likely to occur. Complex sunspot groups, particularly those with mixed magnetic polarities, are especially prone to producing eruptions. Space weather forecasters watch these regions carefully. Historical sunspot observations provided our first glimpse of the solar cycle. Chinese astronomers recorded sunspots over 2,000 years ago. Telescopic observations began with Galileo in 1610. The 11-year cycle was discovered by Heinrich Schwabe in 1843 after decades of patient observations. These long-term observations remain valuable today for studying long-term solar variability. Modern techniques reveal incredible details. High-resolution images show the fine, granular structure of the penumbra. Spectroscopy measures magnetic fields with precision. Helioseismology uses sound waves to probe below spots, revealing how magnetic roots extend thousands of kilometers down into the solar interior. Sunspots also revealed that the sun isn't a solid body. By tracking how spots move across the solar surface, astronomers discovered differential rotation. The equator rotates faster than the poles. This discovery was fundamental to understanding that the sun is made of plasma, not solid material, and that its interior is in constant motion. Each sunspot is a window into the magnetic processes driving solar activity. They're the most visible manifestations of the solar dynamo, the places where intense magnetic fields break through the surface. And though they appear dark in contrast with the surrounding sun, they still glow with temperatures intense enough to vaporize anything that dares approach too closely. 25. Solar flares. Releasing energy of billions of nuclear bombs. What releases more energy in 10 minutes than all of human civilization has used in its entire history? A single powerful solar flare. These sudden explosions of radiation and energy released from the sun's surface are the most violent events regularly observed in the solar system, releasing energy equivalent to billions of nuclear bombs within minutes. Solar flares are classified by their X-ray intensity. The classification goes from A, the smallest, to B, C, M, and X, the most powerful, with each letter representing a 10-fold increase in X-ray brightness. Within each class, there's a numerical scale from 1 to 10. An X2 flare is twice as powerful as an X1. The most powerful flares ever recorded were in the X28 to X45 class. The energy released by a large solar flare is hard to comprehend. A typical X-class flare releases about 6x1025 joules of energy. To put this in perspective, that's equivalent to about 6 billion megaton hydrogen bombs. It's approximately 1/6 of the total energy the sun radiates in all directions in one entire second. The largest flares release even more. The flare of November 4, 2003, initially estimated at X28 but later revised to X45, released about 5x1026 joules. That single event released more energy than all of humanity has consumed in the last decade, and it happened in less than an hour. Where does all this energy go? A large part is emitted as electromagnetic radiation across the entire spectrum. X-rays and extreme ultraviolet light dominate, but flares also produce radio waves, visible light, and sometimes even gamma rays. This radiation travels at the speed of light, reaching Earth in just 8 minutes. Part of the energy goes into heating plasma. The flare region heats to temperatures of 10 to 40 million degrees Celsius, several times hotter than the sun's center. Plasma at these temperatures emits intense X-rays, which is how we detect and measure flares. The superheated region appears as a bright point in X-ray images. Significant energy also goes into accelerating particles. Protons, electrons, and heavier ions are accelerated to near-light speeds. Some particles reach energies of billions of electron volts. These energetic particles can travel through space, creating radiation storms that are dangerous to astronauts and damage satellites. The mechanism behind flares is magnetic reconnection. Magnetic fields in the solar atmosphere sometimes become so twisted and stressed they undergo sudden rearrangement. When oppositely directed magnetic field lines meet and reconnect, stored magnetic energy is explosively converted into other forms: heat, motion, and particle acceleration. Flares occur in active regions, areas of the solar surface with particularly strong and complex magnetic fields, usually marked by sunspot groups. The more complex the magnetic field, the higher the likelihood and potential strength of a flare. The most productive active regions can produce dozens of flares over days or weeks. A flare's anatomy is complex. It begins with a precursor phase where brightening starts to increase. Then comes the impulsive phase, where energy is released most rapidly and X-ray brightness increases dramatically. Finally, there's a gradual decay phase where superheated plasma cools and emission decreases over minutes to hours. Flares often, but not always, are accompanied by coronal mass ejections, CMEs. Large flares and large CMEs often occur together because both result from magnetic instabilities. But the relationship isn't one-to-one. Some large flares don't produce CMEs, and some CMEs occur without significant flares. Flares' effects on Earth vary depending on their intensity and direction. X-ray radiation increases ionization in Earth's upper ionosphere, disrupting shortwave radio communications. This is called a radio blackout and can last from minutes to hours. Aircraft flying polar routes may experience communication disruptions. Energetic particles from flares travel slower than light, taking minutes to hours to reach Earth. When they arrive, they can penetrate satellites, potentially causing damage to electronics or cumulative radiation effects on solar panels. Astronauts outside Earth's magnetosphere protection, like those on future lunar missions, would need to seek shelter during large proton storms. The largest flare ever recorded with modern instruments was the Carrington event of 1859, though we didn't have X-ray measurements then. In the space age, the November 4th, 2003 flare holds the record. It was so powerful it saturated X-ray sensors, which weren't designed to measure something so intense. Flares also produce shock waves that travel through the solar corona. These waves, detectable in ultraviolet images, propagate like ripples in a pond, but at velocities of hundreds of kilometers per second. They can trigger secondary eruptions at distant locations, creating a cascade effect across the solar surface. Predicting flares remains challenging. We can identify active regions that are prone to producing flares based on their magnetic configuration. But predicting the exact timing and magnitude of a specific flare is still beyond our capabilities. The processes that trigger magnetic reconnection operate on timescales of seconds to minutes, giving little warning. 26. The sun's core spins 4 times faster than its surface. The sun hides a secret in its depths. While the surface takes about 25 days to complete one rotation at the equator, the core spins 4 times faster, completing one rotation in approximately 7 days. This radical differential rotation, discovered only recently through sophisticated techniques, reveals complex internal dynamics we're only beginning to understand. For decades, scientists knew the sun's surface doesn't rotate as a solid body. The equator completes one rotation in about 25 days, while polar regions take about 35 days. This differential rotation was discovered by tracking sunspots and other features across the visible surface. But what happens inside the sun remained a mystery. The sun's core is inaccessible to direct observation. It's buried beneath 700,000 kilometers of dense, opaque plasma. No light escapes from it directly. Photons generated in the core take tens to hundreds of thousands of years to diffuse outward until finally emerging from the surface. How could anyone possibly measure the core's rotation? The answer came from helioseismology, the study of sound waves in the sun. Just as geologists use seismic waves to study Earth's interior, helioseismologists use acoustic waves to probe the sun's interior. These waves are generated by turbulent convective motions near the surface and travel through the solar interior. Different wave modes penetrate to different depths. Some modes stay trapped near the surface. Others plunge deep, passing near the core before reflecting back to the surface. By measuring these modes' frequencies and how they change, scientists can infer interior properties, including temperature, density, composition, and rotation. In 2017, an international team of researchers announced a remarkable discovery. Analyzing 16 years of data from the SOHO spacecraft, they detected wave modes that penetrate all the way to the core. These modes are incredibly weak and difficult to detect, but with enough data and careful analysis, they emerge from the noise. The frequencies of these deep wave modes reveal that the core is rotating much faster than the surface. The rotation rate in the core is approximately 1 rotation every 7 days, compared to 25 days at the surface equator. This represents nearly a 4-fold speed difference. Why does the core spin so much faster? The most likely explanation involves the sun's evolutionary history. When the sun formed 4.6 billion years ago from a collapsing cloud of gas and dust, it was spinning faster. As material collapsed, conservation of angular momentum made the rotation speed up, like an ice skater spinning faster when pulling in their arms. Over billions of years, the sun's surface rotation slowed down. The solar wind carries away angular momentum, gradually breaking the outer layers. Magnetic interactions between the sun and its protoplanetary disk in the first millions of years also removed angular momentum, but these forces affect mainly the outer layers. The core, deeply buried and only weakly coupled to the outer layers, retained more of its original angular momentum. It's as if the core remembers the sun's youthful fast rotation, while the surface has been braked by age and angular momentum lost to space. The transition between the fast-rotating core and the slower-rotating surface isn't abrupt. It occurs through a transition layer called the tachocline, located at the boundary between the inner radiative zone and outer convection zone, about 70% of the way from center to surface. The tachocline is a region of strong shear, where rotation velocity changes rapidly with radius. This shear region is crucial for the solar dynamo, the process that generates the sun's magnetic field. Rotational shear in the tachocline stretches and intensifies magnetic fields, helping create the strong magnetic fields we see in sunspots. Without the differential rotation between core and surface, the solar cycle would likely be very different or perhaps not exist. The discovery also has implications for understanding other stars. If the sun has a fast rotating core, other sun-like stars probably do too. This affects models of stellar structure, evolution, and magnetic field generation. Asteroseismology, the study of oscillations in other stars, can potentially detect similar differential rotation in distant stars. Measuring the core's rotation was a technical triumph. The waves that penetrate to the core have periods of several hours and incredibly small amplitudes, just a few centimeters at the sun's surface. Detecting these tiny oscillations requires years of continuous observations and sophisticated data analysis techniques. The core's fast rotation also has implications for the sun's neutrino flux. Neutrinos are subatomic particles produced by nuclear fusion reactions in the core. They escape the sun immediately, taking only seconds to travel from core to space. Detectors on Earth measure the neutrino flux, providing direct information about conditions in the core. Understanding how rotation varies from core to surface helps complete the picture of how the sun works. The sun isn't a simple sphere of gas rotating uniformly. It's a complex, layered structure with different regions spinning at different speeds, interacting through magnetic and hydrodynamic processes. The fast-rotating core is just one piece of this puzzle, but a crucial piece revealing the sun's dynamic history and internal complexity. 27. Alfvén waves, magnetic ripples, carrying energy outward. Imagine waves traveling through plasma at velocities of hundreds of kilometers per second, carrying energy along magnetic field lines like surfers on an ocean wave. Alfvén waves are one of the most important mechanisms for transporting energy from the sun's surface to the superheated corona, and their discovery in the solar corona solved a decades-old mystery about how the sun's atmosphere maintains its million-degree temperatures. Alfvén waves were theoretically predicted by Swedish physicist Hannes Alfvén in 1942. He proposed that in magnetized plasma, waves could propagate along magnetic field lines. These waves involve oscillations of the magnetic field itself and the plasma coupled to it. For this and other contributions to plasma physics, Alfvén received the Nobel Prize in 1970. The waves work through the interaction between magnetic fields and ionized plasma. When a magnetic field line is disturbed, it acts like a stretched string. The disturbance travels along the line at the Alfvén speed, which depends on magnetic field strength and plasma density. In the solar corona, where the magnetic field is strong and plasma is tenuous, Alfvén waves can travel at 1,000 kilometers per second or more. For decades, scientists suspected Alfvén waves could heat the solar corona. The coronal heating problem, why the sun's atmosphere is hundreds of times hotter than the surface, requires an energy source. Waves generated by turbulent motions near the solar surface could propagate upward, carrying energy to the corona. There, waves could dissipate their energy, heating the plasma. But detecting these waves in the corona was challenging. The corona is optically thin, meaning it's transparent. Alfvén waves don't necessarily produce obvious brightness changes that would be easy to observe. Subtle signals needed to be detected in high temporal and spatial resolution data. Advances in the 2000s finally provided definitive evidence. Observations from ground-based and satellite solar telescopes revealed oscillations in coronal structures that matched the expected characteristics of Alfvén waves. Coronal loops, enormous arcs of plasma following magnetic field lines, were seen oscillating and twisting in ways consistent with waves propagating along them. The Parker Solar Probe, launched in 2018, provided even more compelling direct evidence. Flying through the solar corona closer to the sun than any previous spacecraft, it measured magnetic fields and plasma in situ. Instruments detected sudden reversals in magnetic field direction, called switchbacks, which are signatures of large amplitude Alfvén waves. These observations confirm that Alfvén waves are abundant in the solar corona. They carry substantial energy. But the critical question remains, is this energy dissipated efficiently enough to explain coronal heating? The answer appears to be yes, at least partially. Alfvén waves can dissipate energy through several mechanisms. When waves have small spatial scales, plasma resistivity causes them to decay, converting wave energy to heat. Turbulence can make waves interact and cascade to smaller scales where dissipation is more efficient. And when waves travel through regions of varying density or magnetic field, they can undergo resonant damping. One particularly important feature of Alfvén waves is that they can accelerate the solar wind. As waves propagate outward through the corona, they exert pressure on the plasma. This pressure can accelerate plasma outward, contributing to solar wind acceleration from low velocities near the Sun to the supersonic velocities of 300 to 800 kilometers per second observed farther out. Observations of coronal holes, regions where magnetic field lines are open to interplanetary space rather than closed in loops, show particularly strong evidence of Alfvén waves. These regions are sources of fast solar wind, and Alfvén waves have been detected carrying energy and momentum outward, driving the wind. Waves also appear in other solar structures. Spicules, those plasma jets shooting upward from the chromosphere, show signs of Alfvén waves propagating along them. Solar prominences, large structures of plasma suspended in the corona, exhibit oscillations consistent with Alfvén waves. The entire Sun appears permeated with these magnetic waves. The amount of energy transported is substantial. Estimates suggest the Alfvén energy flux in the low corona is about 100 to 1,000 watts per square meter. Multiplied by the Sun's surface area, this totals about 10 to 23 up to 10 to 24 watts. This is more than enough to provide the heating necessary to maintain the corona at millions of degrees. But converting this wave energy flux into effective heating requires that waves dissipate their energy in the corona, not simply escape to space. Understanding exactly where and how this dissipation occurs remains an active research area. Different corona regions may be heated by different mechanisms, with Alfvén waves playing varying roles. Alfvén waves also occur in other planetary magnetospheres and in astrophysical plasmas everywhere. In Earth's magnetosphere, they're generated by interactions with the solar wind and can transfer energy to the ionosphere, contributing to auroras. In experimental fusion plasmas, controlling Alfvén waves is important for containing hot plasma. On the Sun, these waves represent a fundamental connection between the surface and corona. Turbulent motions in the photosphere and chromosphere generate waves that propagate upward. These waves carry energy through the solar atmosphere. When they dissipate, they heat plasma and accelerate the solar wind. It's an elegant energy transport system, carried by magnetic oscillations traveling along the coiled and twisted magnetic fields permeating the Sun's atmosphere. 28. The solar wind's sudden acceleration. Beyond the corona, the solar wind begins its journey very slowly, but something mysterious happens. Within just a few solar radii distance, it suddenly accelerates from subsonic to supersonic velocities, reaching hundreds of kilometers per second. What causes this dramatic acceleration has been one of solar physics' long-standing mysteries, and only recently have we begun understanding the processes involved. In the low corona, near the Sun's surface, plasma is moving outward at just a few tens of kilometers per second. This velocity is less than the sound speed in hot coronal plasma, which is about 100 to 200 kilometers per second. Plasma is flowing outward, but relatively slowly, still strongly bound to the Sun by gravity. But somewhere between about 2 and 10 solar radii from the surface, something dramatic happens. Plasma accelerates rapidly. Within a relatively short distance, the solar wind reaches 300 to 800 kilometers per second, depending on whether it's slow or fast solar wind. This velocity is several times the sound speed in plasma, making the flow supersonic. What provides the energy for this acceleration? Simple thermal expansion isn't enough. If you calculated how fast hot coronal plasma should expand based solely on its temperature and pressure, you get velocities of maybe 100 to 200 kilometers per second at Earth's orbit. But the actual solar wind is much faster, especially the fast solar wind from coronal holes. A clue comes from spacecraft observations. The Ulysses probe, which orbited over the Sun's poles in the 1990s, measured solar wind at different latitudes. It found that fast solar wind originating from coronal holes at the poles reached velocities of 700 to 800 kilometers per second. This wind also had a specific temperature. It was cooler than expected for its velocity. If wind were simply heated and then expanded, faster plasma should be hotter. but fast solar wind is actually cooler than slow wind. This suggests energy is being added to the wind not as random heat, but as directed outward motion. Something is pushing or pulling the plasma to accelerate beyond what thermal expansion alone would produce. Alfvén waves emerged as leading candidates. As discussed earlier, these magnetic waves carry energy upward along magnetic field lines, but they can also accelerate plasma. Alfvén waves exert a force called wave pressure or magnetic radiation pressure. This force pushes plasma in the direction of wave propagation. In regions of decreasing magnetic field, Alfvén waves can deposit their momentum into plasma, accelerating it outward. This process is particularly efficient in coronal holes, where magnetic field lines are open to interplanetary space and diverge rapidly. The expanding geometry amplifies the wave's acceleration effect. The Parker Solar Probe provided direct evidence of this process. Flying through the region where acceleration occurs, it measured abundant Alfvén waves and correlations between wave amplitude and wind velocity. Regions with stronger waves showed stronger acceleration. The data support the idea that waves are an important driver of solar wind acceleration, but waves may not be the whole story. Additional heating in the extended corona may also contribute. If plasma is heated as it moves outward, the increased pressure drives additional acceleration. Possible heating mechanisms include wave dissipation, small-scale magnetic reconnection, and turbulence. The critical point appears to be between 10 and 20 solar radii from the Sun's center. This is where the solar wind transitions from subsonic to supersonic, crossing what's called the sonic or critical point. Once supersonic, the flow can no longer be affected by pressure disturbances from behind and continues accelerating more gradually as it moves outward. Different types of solar wind accelerate at different rates and locations. Fast solar wind from coronal holes accelerates rapidly and reaches high velocities close to the Sun. Slow solar wind from equatorial regions accelerates more gradually and never reaches such high velocities. The difference reflects different magnetic field geometries and perhaps different amounts of heating and wave driving. Understanding solar wind acceleration has practical implications. The solar wind carries magnetic field and energetic particles that affect Earth and other planets. Predicting solar wind velocity and density is crucial for space weather forecasting. Models that correctly incorporate acceleration physics can make better predictions. Acceleration also represents efficient conversion of thermal and magnetic energy into bulk kinetic energy. The solar wind removes angular momentum from the Sun, probably slowing solar rotation over billions of years. It carries magnetic field into space, creating the heliosphere that extends well beyond Pluto. Future observations from the Parker Solar Probe, as it continues diving closer to the Sun, and from the Solar Orbiter, which observes from different perspectives, should provide more details. These missions are measuring solar wind in its source regions, where acceleration processes operate, providing unique insights. The solar wind's sudden acceleration demonstrates that the corona isn't just a hot, static atmosphere. It's a dynamic region where plasma is constantly flowing outward, being heated and accelerated by processes we're only beginning to unravel. The wind that finally reaches Earth at millions of kilometers per hour began its journey much more humbly, then gained speed through a critical region where waves, magnetic fields, and heating conspire to launch it into the solar system. 29. The Sun's mysterious silent periods, the Maunder minimum. What if the Sun simply stopped? Not stopped shining, but stopped its normal activity cycle, ceased producing sunspots, and entered a state of deep quietude for decades. This actually happened. From 1645 to 1715, during a period called the Maunder minimum, the Sun entered an extraordinary state of low activity, with sunspots nearly disappearing for 70 years. During the normal solar cycle, sunspot numbers vary from nearly zero at solar minimum to 100 to 200 or more at solar maximum. But during the Maunder minimum, sunspots were extremely rare for 7 consecutive decades. Some years had no visible spots, others had just 1 or 2. Observers of the time commented on the strange absence of these familiar features. The period is named for astronomer Edward Maunder, who in 1890 studied historical sunspot records and recognized this anomalous period. He noted that records from astronomers like Giovanni Cassini showed sunspots were extremely scarce, and those that appeared were confined to the Sun's southern hemisphere, a very unusual distribution. Initially, some scientists questioned whether the Maunder minimum was real or simply an artifact of poor observations. Perhaps people weren't looking carefully, but independent evidence confirmed it was a real phenomenon. Aurora records show auroras were extremely rare during this period. Normally, auroras occur several times per year at mid-latitudes during active periods. During the Maunder minimum, decades passed without aurora sightings. Even more compelling comes from an independent proxy, radiocarbon in tree rings. Cosmic rays hitting Earth's atmosphere create carbon-14. The production rate is modulated by solar activity because the solar magnetic field and solar wind deflect cosmic rays. During periods of high solar activity, fewer cosmic rays reach Earth, and less carbon-14 is produced. During low activity periods, more cosmic rays penetrate and more carbon-14 is created. Tree rings preserve a record of atmospheric carbon-14. Measurements show a clear increase in carbon-14 during the Maunder minimum, confirming the Sun was indeed in a very low activity state. The solar magnetic field was weak, solar wind was reduced, and more cosmic rays were hitting Earth. What caused this prolonged state of low activity? Nobody knows for certain. The solar dynamo, the process that generates the Sun's magnetic field, apparently entered a different mode of operation. Perhaps internal circulation changed. Perhaps the tachocline, the shear region between the fast-rotating core and convective envelope, was disturbed somehow. Computer models of the solar dynamo suggest it may have multiple stable states. The normal state produces the 11-year cycle we observe most of the time. But under certain conditions, the dynamo can enter a grand minimum state where magnetic field generation is dramatically suppressed. Transitions between these states might be triggered by random fluctuations in the Sun's internal flows. Interestingly, the Maunder minimum coincided with the coldest part of the Little Ice Age in Europe. From about 1300 to 1850, global temperatures were about 0.5 to 1 degree Celsius cooler than today. The coldest period was during the Maunder minimum. Rivers that rarely froze began freezing regularly. Glaciers advanced, crops failed more frequently. The connection between the Maunder minimum and cold climate remains debated. The Sun's total energy output varies only about 0.1% over the 11-year solar cycle. During a grand minimum, the change might be slightly larger, perhaps 0.2 to 0.3%. This seems too small to explain the observed cooling by itself, but indirect mechanisms might amplify the effect. During periods of low solar activity, more cosmic rays hit Earth's atmosphere. Some scientists propose that increased cosmic rays could affect cloud formation, potentially increasing cloud cover. More clouds would reflect more sunlight, causing cooling. This hypothesis remains controversial and not fully tested. The Maunder minimum wasn't unique. Radiocarbon records reveal other grand minima in the past. The Sporer minimum occurred from 1450 to 1540. The Dalton minimum was from 1790 to 1820, though less deep than the Maunder. The Wolf minimum occurred from 1280 to 1350. These events seem to happen irregularly, perhaps every few centuries. There are also grand maxima, periods of unusually high solar activity. The 20th century, particularly from 1940 to 2000, was a grand maximum. The Sun was more active during this period than at any time in the previous 8,000 years based on radiocarbon records. Some scientists suggest we're now entering a period of declining solar activity. The current solar cycle, cycle 25, began relatively weak. Some predicted it might lead to another grand minimum. But long-term predictions of solar dynamo behavior are uncertain. We may be entering a period of reduced activity, or the Sun may return to normal activity in upcoming cycles. If another Maunder minimum occurred today, the implications would differ from those of the 17th century. Climatically, any solar cooling would be small compared to anthropogenic warming from greenhouse gas emissions. But for space weather, it would be significant. Fewer geomagnetic storms would mean fewer threats to satellites and power grids, but also fewer spectacular auroras. 30. The Sun's Oscillations. It rings like a bell. The entire Sun is vibrating, not just swaying slightly, but resonating with millions of different frequencies simultaneously, like a giant bell struck by an invisible hammer. These oscillations make the entire solar surface move up and down in complex overlapping patterns, creating a symphony of motions that scientists can now detect and interpret. If you could see the oscillations directly, you'd see the entire solar surface moving in a kaleidoscopic pattern. Some regions would be moving upward while adjacent regions move downward. The patterns would constantly change, with waves traveling across the surface and interfering with each other. It's like watching a water surface during a storm, but on a sphere the size of 1,000,000 Earths. The amplitudes are surprisingly small. The surface rises and falls just a few kilometers, less than 1,000th of the Sun's radius. For an object 1.4 million kilometers in diameter, this is tiny. It's as if a basketball were vibrating with amplitudes smaller than the thickness of a human hair. Yet these tiny oscillations are detectable and informative. The oscillation velocities are larger, typically a few hundred meters per second. Scientists detect these oscillations by measuring Doppler shifts in sunlight. When a surface region moves toward us, light is slightly shifted toward blue. When it moves away, it's shifted toward red. By measuring these shifts at many surface points, scientists can map the oscillation patterns. The most prominent mode has a period of about 5 minutes. It corresponds to acoustic waves trapped in the Sun's outer convection zone. These waves reflect from the surface, where density drops abruptly, and from a depth of about 200,000 kilometers below the surface, where temperature increases enough to refract waves back upward. But the 5-minute mode is just the easiest to detect. Actually, there are millions of oscillation modes. Each mode has a specific frequency, a specific spatial pattern on the surface, and penetrates to a specific depth. Modes are classified by 3 numbers: the number of radial nodes, how many times amplitude goes to 0 along a radius from center to surface; the spherical harmonic degree, how many patterns exist around the surface; and the azimuthal number, the pattern's orientation. Detecting all these modes requires long, continuous observations. Gaps in observations, like when the sun sets, create aliases and make identifying frequencies difficult. To overcome this, networks of telescopes around the world observe the sun continuously. When the sun sets at one location, another telescope takes over, providing 24-hour coverage. Space observatories like SOHO provide truly uninterrupted observations. By analyzing the frequencies of millions of modes, scientists can reconstruct the sun's internal structure. Different modes are sensitive to different regions. High-degree modes, many-surface patterns, stay trapped near the surface. Low-degree modes penetrate deep into the interior. By comparing observed frequencies with theoretical predictions, scientists can test and refine models of solar structure. Helioseismology revealed many surprises. It confirmed the sun's core is rotating faster than the surface, as discussed earlier. It showed the convection zone extends down to about 30% of the solar radius, deeper than some models predicted. It revealed jet streams below the surface, zonal flows analogous to those in Earth's atmosphere. Oscillations also change with the solar cycle. During solar maximum, oscillation frequencies shift slightly, a few millionths of a hertz. These changes reflect alterations in magnetic field and thermal structure near the surface. By tracking these changes, scientists can monitor internal conditions as the sun progresses through its activity cycle. Asteroseismology, applying these techniques to other stars, has become a powerful tool. Space missions like Coronal and Kepler detected oscillations in thousands of stars. By analyzing these oscillations, astronomers determine masses, radii, ages, and internal compositions of stars throughout the galaxy. Some of these stars have planets, and asteroseismology provides precise host star characterization, crucial for understanding the planets. Solar oscillations never stop. They're continuously excited by turbulent convective motions just below the surface. Convection cells rising and sinking generate acoustic waves randomly. These waves propagate through the interior, reflecting and refracting, creating interference patterns that manifest as the millions of observed oscillation modes. Imagine striking a giant bell not once, but with millions of tiny hammers, continuously and randomly tapping. The bell would ring with many frequencies simultaneously, creating a complex sound rich in harmonics. That's how the sun oscillates, a cosmic bell rung by the turbulence of its own convective interior, resonating with frequencies that reveal secrets from its hidden depths. 31. Coronal holes. Dark regions that aren't holes. What looks like a hole in the sun actually isn't a hole. Coronal holes appear as dark regions in ultraviolet and X-ray images of the solar corona, But they're not empty regions. They're areas where the magnetic field has a different configuration, allowing plasma to escape easily into space, creating the high-speed solar wind that can reach Earth and trigger auroras. In visible light images, coronal holes are invisible. The sun's surface looks normal in these regions, but at ultraviolet and X-ray wavelengths, which reveal the hot corona, coronal holes appear dramatically dark. They can cover enormous areas, sometimes a quarter or more of the solar disk. They look empty, but they're actually filled with plasma, just cooler and less dense plasma than the surrounding corona. The key to understanding coronal holes lies in the magnetic field. In most of the corona, magnetic field lines form closed loops. A magnetic field emerges from the surface at one location, arcs through the corona, and plunges back down at another location. Plasma gets trapped in these loops, heated to millions of degrees, creating the bright corona. In coronal holes, the magnetic topology is different. Magnetic field lines are open, extending from the solar surface outward into interplanetary space without looping back. This open configuration allows plasma to escape easily along field lines. The result is that less plasma accumulates, density is lower, and the region appears darker. But this open configuration also has another important consequence. Plasma flowing along open field lines can accelerate efficiently away from the sun. Coronal holes are the source of high-speed solar wind. While slow solar wind from the equator travels at 300 to 400 kilometers per second, fast solar wind from coronal holes reaches 700 to 800 kilometers per second. Coronal holes aren't permanent. They evolve and change over days, weeks, and months. Small coronal holes can appear and disappear within days. Large polar coronal holes can persist for years, especially during solar minimum. During solar maximum, coronal holes tend to be smaller and more transient, often located at lower latitudes. The distribution of coronal holes changes with the solar cycle. During solar minimum, large coronal holes dominate polar regions, and equatorial holes are rare. During solar maximum, polar holes shrink or disappear, and smaller holes appear at all latitudes. This shift reflects the reorganization of the sun's global magnetic field throughout the solar cycle. When a coronal hole faces Earth, a stream of high-speed solar wind hits our planet a few days later. This high-speed stream compresses the magnetosphere, triggering moderate-level geomagnetic storms. These storms cause auroras, especially at high latitudes, and can last several days as Earth is bathed in the high-speed stream. Rotating coronal holes create recurring patterns. As the sun rotates, with a period of about 27 days as seen from Earth, a coronal hole facing Earth eventually rotates away, then returns about 27 days later. This creates recurring geomagnetic storms, storms that appear at roughly monthly intervals while the coronal hole persists. Observations from the Parker Solar Probe flying through coronal holes provided unprecedented insights. The spacecraft measured less dense plasma, stronger and more open magnetic field, and abundant Alfvén waves. The data confirm that waves are likely important for accelerating fast solar wind in these regions. Coronal holes also emit less ultraviolet and X-ray radiation because plasma is cooler and less dense. Temperatures in coronal holes are about 1 to 1.5 million degrees, compared to 2 to 3 million degrees in the normal corona. This temperature difference, combined with lower density, makes coronal holes appear dark in images. Why do some magnetic fields form closed loops while others are open? The answer lies in the global magnetic field configuration and the distribution of smaller magnetic fields on the surface. Where fields of opposite polarity are nearby, they tend to connect in loops. Where fields of one polarity dominate without nearby opposite polarity sources to connect to, field lines extend into space, creating a coronal hole. Predicting coronal holes is important for space weather forecasting. When a large coronal hole is about to rotate to face Earth, space weather forecasters can predict the arrival of high-speed solar wind days in advance. This provides time for satellite operators and power grid operators to prepare for possible disturbances. Coronal holes demonstrate that what appears dark can actually be more active. These empty regions are actually portals where the sun is gushing plasma into space at supersonic velocities. They're direct connections between the solar surface and interplanetary space, highways for the solar wind that eventually fills the entire solar system and defines the heliosphere's boundaries. 32. The sun's magnetic poles, reverse. every 11 years. Imagine if Earth's magnetic field suddenly reversed with compasses pointing south instead of north. On the Sun, this actually happens regularly every 11 years. The Sun's magnetic poles undergo a complete reversal, with the magnetic North Pole becoming the South Pole and vice versa. It's one of the most dramatic transformations the Sun undergoes, and it happens near the peak of each solar cycle. The reversal isn't instantaneous, it's a gradual process occurring over several months near solar maximum. The magnetic poles weaken, briefly disappear, and then reappear with opposite polarity. During the transition, the Sun's global magnetic field becomes extremely complex and disorganized, with no clear dipolar structure. The process begins with sunspot appearance. Sunspots appear in pairs with opposite magnetic polarities. In the northern hemisphere during one cycle, the leading spot has one polarity, say north, and the following spot has the opposite polarity, south. In the southern hemisphere, the pattern is reversed. Leading spots are south and following spots are north. As sunspots appear, evolve, and decay, their magnetic fields spread out. The following spot's magnetic field tends to migrate toward the poles. Over several years, this sunspot magnetic field accumulates in polar regions. Since following spots have opposite polarity to the existing pole, they gradually cancel out and eventually reverse the polar polarity. For example, say the Sun's north pole has positive polarity magnetic field at a cycle's beginning. Sunspots in the northern hemisphere have positive leading spots and negative following spots. As the negative following spots' fields migrate to the North Pole, they cancel the existing positive field. Eventually, enough negative field accumulates and the pole reverses to negative. The same process happens simultaneously in the southern hemisphere, but with opposite polarities. The net result is that both poles reverse at the same time, maintaining the global dipolar structure, but with reversed polarities. The Sun doesn't develop two north poles or two south poles. The reversal is coordinated. Observing the reversal requires measuring magnetic fields in the Sun's polar regions. This is challenging because Earth orbits near the Sun's equatorial plane, so we see the poles at oblique angles. Ground-based and space solar observatories use magnetographs to measure magnetic field strength and direction on the solar surface. During solar minimum, the polar magnetic field is strong and clearly dipolar, with magnitude of about 5 to 10 Gauss at the poles. As the cycle progresses and sunspots proliferate, the polar field weakens. At solar maximum, it can drop to just 1 to 2 Gauss and become very disorganized. Then, as sunspots begin disappearing, the polar field starts strengthening again, but with reversed polarity. The polar reversal is the midpoint of the Sun's complete 22-year magnetic cycle. It takes two 11-year cycles for everything to return to the original configuration. That's because sunspots also reverse their polarities every cycle. If northern leading spots are positive during one cycle, they're negative the next. The interplanetary magnetic field, the magnetic field embedded in the solar wind, reflects solar magnetic structure. During polar reversal, the interplanetary magnetic field becomes more variable and complex. The organized magnetic sector structure that exists during stable periods gets disturbed. This can affect cosmic rays reaching the solar system and may influence space weather at Earth. The polar reversal affects the entire heliosphere. The Sun's magnetic field extends billions of kilometers, creating a ballerina skirt-shaped structure called the heliospheric current sheet. This sheet marks the boundary between opposite magnetic polarities. During polar reversal, the sheet becomes wavy and complex, creating variable conditions for spacecraft and planets throughout the solar system. Why does the reversal happen? It's a natural consequence of the solar dynamo, the process that generates magnetic fields through convective motions and differential rotation also produces migrating patterns of magnetic field. The mathematical details are complex, but the essence is that the same process creating sunspots also drives polar reversal. Other stars likely undergo similar reversals, though they are very difficult to detect directly. Some evidence comes from long-term monitoring of stellar activity. Sun-like stars show activity cycles that likely reflect underlying magnetic cycles. Direct detection of stellar magnetic fields and their reversals remains at the frontier of observational capability. The Sun's polar reversal is a reminder that our star isn't static. The magnetic field permeating the corona, guiding the solar wind, and creating sunspots is in constant evolution. Every 11 years, the sun reinvents itself magnetically, resetting its poles and beginning a new chapter in its endless cycle of magnetic activity. 33. Solar energetic particles. Reaching 99% the speed of light. The sun doesn't just emit light and plasma, sometimes it shoots individual particles at velocities so close to the speed of light that relativity starts to matter. Solar energetic particles, accelerated by flares and eruptions, can reach energies of billions of electron volts, becoming dangerous radiation that can penetrate spacecraft and pose risks to astronauts. These particles are mainly protons, but include electrons, helium, and heavier ions. In a typical solar energetic particle event, protons are accelerated to energies of 10 million to a few billion electron volts. Protons of 1 billion electron volts are traveling at about 87% the speed of light. The most extreme events produce particles exceeding 10 billion electron volts, with velocities of 99% the speed of light or more. At these velocities, relativistic effects become significant. Particles' mass increases. Time slows down from the particle's viewpoint. Trajectory calculations must use special relativity instead of classical Newtonian mechanics. These are particles moving so fast that normal physics rules start to change. How does the sun accelerate particles to these tremendous energies? Two main processes are involved. The first is magnetic reconnection during solar flares. When magnetic fields reconnect, they create intense electric fields in the reconnection region. Charged particles are accelerated by these electric fields, gaining energy rapidly. The second process involves shock waves. Fast coronal mass ejections create shock waves that propagate through the corona and into interplanetary space. Particles can be caught by these shock waves and repeatedly reflected back and forth, gaining energy with each reflection. This process, called diffusive shock acceleration, can produce particle energy spectra extending to very high energies. Solar energetic particles arrive at Earth in waves. The fastest particles, traveling near light speed, arrive about 8 minutes after the flare, only slightly behind photons. Slower particles arrive over the next hours and days, creating a radiation storm that can last days. These storms' intensity varies enormously. Small events increase particle counts perhaps tenfold above background. Large events increase particle counts 1,000 to 10,000-fold. The most extreme events, called ground-level enhancement events, are so intense that protons penetrate Earth's entire atmosphere and are detectable in ground-based neutron monitors. Only a few ground-level enhancement events have been recorded since monitoring began in 1942. The largest was on February 23, 1956. Another massive event occurred on January 20, 2005. These events produce radiation fluxes that are lethal to unprotected humans in space and dangerous even to people in high-altitude aircraft on polar routes. Astronauts are particularly vulnerable. The International Space Station orbits within Earth's magnetosphere, which provides significant protection. But astronauts on lunar missions outside the magnetosphere would be exposed. During a large solar energetic particle event, they'd need to seek shelter behind shielding, perhaps in a specially protected module or behind large masses of supplies. The Apollo missions were lucky. During the Apollo program from 1968 to 1972, no large solar energetic particle event occurred while astronauts were on the moon. But between Apollo 16 and 17 in August 1972, a large event occurred. If astronauts had been on the lunar surface, they would have received dangerous radiation doses. Satellites are also affected. Energetic particles can penetrate spacecraft and damage electronics. They can cause bit flips in computer memories, degrade solar panels, and damage sensors. Satellites in high orbits, like GPS satellites in 20,000-kilometer orbits, are particularly vulnerable. Predicting solar energetic particle events is challenging. When a large flare erupts, we can predict energetic particles will likely be produced. But predicting intensity and energy spectrum requires understanding particle acceleration details, which still aren't fully understood. Models have improved, but large uncertainties remain. Some solar energetic particles are so energetic they rival galactic cosmic rays, particles accelerated by supernovae and other extreme phenomena beyond the solar system. Distinguishing solar energetic particles from cosmic rays requires careful analysis of composition and arrival patterns. Solar energetic particles arrive in bursts associated with solar events, while cosmic rays provide a constant background. Solar energetic particles' energy spectrum roughly follows a power law. Particle counts decrease rapidly with increasing energy. For every 10 billion electron-volt particle, there are millions of 10 million electron-volt particles. But the fact that any particles reach billion electron-volt energies is impressive, demonstrating solar acceleration processes' efficiency. These particles represent a frontier where solar physics meets high-energy particle physics. Understanding how the Sun accelerates particles to relativistic energies informs not only space weather forecasting, but also understanding of particle acceleration in more extreme astrophysical environments. The Sun is a natural plasma physics laboratory, accessible and observable, performing experiments we cannot replicate on Earth. 34. The Sun's differential rotation, different speeds at different latitudes. The Sun doesn't rotate like a solid ball. Different parts spin at different speeds, with the equator completing one rotation in about 25 days while polar regions take 35 days. This differential rotation, where different latitudes have different rotation periods, is fundamental to generating the Sun's magnetic field and driving the 11-year solar cycle. The discovery of differential rotation goes back to the earliest telescopic observations of sunspots. By tracking sunspots across the Sun's face, astronomers noticed that spots at different latitudes took different amounts of time to return to the same position. Spots near the equator return faster, indicating faster rotation. Modern measurements precisely quantified differential rotation. At the equator, the rotation period is about 25 days. At 30 degrees latitude, it's about 26.5 days. At 60 degrees, it's about 30 days. Near the poles, it's about 35 days or more. There's also evidence of slightly faster rotation in active regions with sunspots, but the general pattern is decreasing rotation with increasing latitude. Why does the Sun exhibit differential rotation? The answer lies in the fact that the Sun is made of plasma, not solid material. In a solid object like Earth, different parts must rotate together because they're mechanically connected. But in a fluid or plasma, different parts can move independently. Differential rotation results from the interaction between rotation and convection. The Sun's outer convection zone is constantly in motion, with hot plasma rising and cooler plasma sinking. These convective motions interact with global rotation, creating complex flow patterns that result in rotation velocities varying with latitude. Mathematically, the process involves conservation of angular momentum and Coriolis forces. As plasma moves radially, inward or outward, and meridionally, north-south due to convection, Coriolis forces deflect this motion, creating zonal, east-west flows. The net result is differential rotation. Differential rotation isn't just superficial. Helioseismology revealed it extends through the convection zone. At depths up to about 200,000 kilometers below the surface, differential rotation continues with similar patterns. But at greater depths in the radiative zone, rotation changes to rigid body rotation, where all latitudes rotate together. The transition occurs at the tachocline, a thin layer at the boundary between the radiative and convective zones. The tachocline is only about 3% of the solar radius thick, but plays an enormous role in the solar dynamo. Rotational shear in this layer, where the differentially rotating convective zone meets the rigid body radiative zone, is ideal for generating and amplifying magnetic fields. The solar dynamo works through two main processes. First, differential rotation takes poloidal, north-south running magnetic fields and stretches them in the toroidal, east-west direction. This amplifies field strength. Second, helical convective motions twist toroidal fields, reconverting them to poloidal fields with opposite polarity. This combination of processes creates an oscillating dynamo, where the magnetic field grows, reverses polarity, and grows again in a cycle. Without differential rotation, the dynamo wouldn't work the same way, and the Sun probably wouldn't have the 11-year cycle of magnetic activity. Differential rotation also creates latitude patterns in solar features. Sunspots first appear at mid-latitudes at a solar cycle's beginning and migrate toward the equator as the cycle progresses. This pattern, called Spurer's law or the butterfly diagram when plotted, results from where magnetic fields generated by differential rotation become buoyant and emerge at the surface. Observations revealed additional features. There's evidence of jet streams below the surface, zonal flows that flow faster or slower than average rotation. These jet streams migrate in latitude during the solar cycle, possibly related to sunspot migration toward the equator. Helioseismology also detected rotation variations with the solar cycle. During solar maximum, differential rotation changes slightly. These changes are small, about 1 to 2%, but measurable, and indicate that magnetic activity affects the convective flows driving differential rotation. Differential rotation isn't exclusive to the Sun. Jupiter, Saturn, and other giant planets also exhibit differential rotation, with equators spinning faster than polar regions. Other stars likely have differential rotation too. Detecting it requires sophisticated techniques like Doppler spectroscopy or Doppler imaging, but some measurements have been made. The Sun's differential rotation is one of the fundamental processes that makes the Sun a dynamic and magnetic object. Without it, there would be no solar cycle, few sunspots, and far fewer flares and CMEs. It's a reminder that the Sun isn't a simple sphere, but a complex system where internal flows and magnetic fields interact to create the rich variety of phenomena we observe. 35. Solar prominence eruptions. Lasting months. Imagine plasma structures the size of planets suspended above the Sun's surface, floating in magnetic fields, persisting for weeks or even months. Solar prominences are some of the most spectacular structures in the solar atmosphere. Giant arcs of relatively cool plasma suspended in the superheated corona. And when they erupt, they launch billions of tons of material into space in dramatic events that can last hours. Prominences appear as bright structures above the Sun's edge when observed in ultraviolet or hydrogen alpha light. They consist of plasma about 10 times denser than the surrounding corona and much cooler, about 10,000 degrees, instead of 1 million degrees. How can such cool, dense structures exist in the hot corona without falling back to the surface or heating up and dissipating? The answer is magnetic fields. Prominences are supported by magnetic fields acting like invisible hammocks. Fields form arched or dome-shaped structures that can sustain dense plasma's weight against solar gravity. Plasma gets trapped around these magnetic structures, following field lines. Prominences can be enormous. Typical quiescent prominences extend 100,000 to 200,000 kilometers above the surface, with lengths along the surface up to 500,000 kilometers. That's large enough that Earth could fit comfortably inside many prominences. The largest observed prominences exceeded 800,000 kilometers in height, more than half the Sun's diameter. Quiescent prominences are stable and long-lasting. They can persist for weeks, even months, floating gracefully above the surface. Observations show plasma flowing along them, descending toward the surface in thin threads, while new material flows upward from below, maintaining the structure. But prominences don't always remain calm. They can become unstable and erupt. When the underlying magnetic structure changes or becomes unstable, the equilibrium holding the prominence can be disturbed. The prominence begins rising, accelerating as magnetic fields reconnect below it. Within hours, the entire structure is launched into space. Prominence eruptions are spectacular. The plasma mass, sometimes billions of tons, rises at increasing velocities. Typical eruptions reach velocities of 200 to 400 kilometers per second. Extreme eruptions exceed 1,000 kilometers per second. The rising plasma appears as an expanding arc in images, climbing through the field of view over hours. Prominence eruptions often accompany coronal mass ejections. In fact, many CMEs contain prominence material. Dense prominence plasma provides the bright core often observed in CME images. When a CME reaches Earth, instruments sometimes detect unusual compositions or temperature signatures that trace back to the original prominence. Why do prominences erupt? The answer involves magnetic energy storage and release. As magnetic fields below a prominence are sheared and twisted by photospheric motions, they store energy. Eventually, the configuration becomes unstable. The prominence begins rising, triggering magnetic reconnection below it, which releases energy and drives the prominence upward faster. Not all eruptions succeed. Sometimes a prominence begins erupting but then falls back. These failed eruptions occur when the overlying magnetic field is strong enough to contain the rising prominence. The prominence reaches a certain height, stops, and then falls back, often reforming in the same position. High-resolution images reveal complex internal structure. Prominences aren't uniform clouds but consist of thin threads and sheets of plasma. These threads, some just hundreds of kilometers wide, follow individual magnetic field lines. Time-lapse images show plasma flowing along these threads in intricate patterns. Some prominence types are more prone to erupting. Filaments, prominences seen against the solar disk instead of at the edge, in complex magnetic active regions often erupt. These active prominences are less stable than quiescent prominences in quiet regions. They may erupt within hours to days of forming. The longest-lived observed prominences lasted several months, rotating with the Sun through multiple rotations. These persistent prominences usually form along polarity inversion lines, boundaries between regions of opposite magnetic field. The magnetic configuration along these lines favors stable, long-lasting prominence formation. When prominences erupt, they leave dark cavities in the corona. These cavities, regions of reduced density where the prominence was, can persist for hours to days before filling in. They appear as dark regions in coronal images, similar to coronal holes but transient. Prominences demonstrate the complex interplay between plasma and magnetism on the Sun. They're structures where gravity, plasma pressure, and magnetic forces reach a delicate balance. When that balance is disturbed, structures containing planetary masses of plasma are hurled into space, traversing the solar system and occasionally impacting Earth. They're reminders that even the Sun's seemingly stable features can erupt violently, changing from serene to explosive within hours.